So I'm going to tell you a little bit about OpenMP offload programming. Actually, most of what I say is, and you probably saw it from the background that I quickly replaced with the AMD one, that I have some ties into the OpenMP programming models. I'm actually the CEO of the OpenMP Architecture Review Board, so I'm leading that standards body. But I'm also, my daytime job is at AMD as a principal member of technical staff, where I work as we call it senior field application engineer. So someone who takes care of all the technical questions, problems, prototypes, and other hand-holding that is required to make our customers happy customers. And I do that in the HPC Center of Excellence. And there I'm actually mostly spending my time on GPU topics, but with my long background in CPUs, I'm quite frequently also touching these subjects. All right, so agenda. The 4 things that I would like to do is show how to effectively avoid data transfers with OpenMP directives, talk a little bit about asynchronous offloading. I think that ties kind of nicely into what you heard the last 3 days about HIP and how it has this asynchronity built in when you do a kernel launch. We have a similar concept in OpenMP. Then I want to show you how you can use hybrid programming with both OpenMP and HIP in both ways, actually. So coming from the OpenMP world, invoking HIP as kind of an optimization target, or the other way around, starting from HIP code and then going into the OpenMP world to gradually roll back HIP and replace it with OpenMP again, so that you have a nice high productive programming model again. And then, integrating asynchronous programming models. Let's see if I can get to it. If not, I'll be happy to, share some insight also over email. This is more meant to, also talk to something like HIP from another OpenMP angle. All right, there's a running example that I would like to use for this slide deck. It's nice and crisp. It's Saxby. It's one of the, I would call them HPC dwarfs. So the blue part down here, parallelized through OpenMP on the host, that's the stuff that we want to eventually run on a GPU. And the green part is just to have a little more meat on my slide, and also to have some low-man's timing code around that. And you can see it's actually not the real Sax, because I'm kind of having that as a self-contained function that doesn't take any arguments, and we will go through and refine them over time. The word of caution that I would like to make, though, is don't do this at home. There's libraries for that. So ROCblast or HipBlast comes to mind, that has an optimized version of that for GPUs, and then obviously AMD Bliss, who has the same kind of functionality for EPYC processors. All right, but let's bring this over to the GPU, and let's just ignore that word of advice for a minute. All right, so this is very simplistic. This is how you can get it over to the GPU. So basically, you prefix everything with pragma on target. I replaced the multi-threading directive and replaced it with a GPU offload directive. And then the compiler, when invoked with that command line, and actually there's a dash missing, so I'm sorry about that, will move that stuff over to the GPU. So the encountering thread at some point will reach this OpenMP target directive. It will send control flow over to the target device. It will run on the target device, and then it will come back after the closing curly brace, and when the loop is done and the kernel has finished because of that, and then continue executing the green part down here, printing the timing part. And what you can already see is that by default, the OpenMP offload model is synchronous. So there's actually a gap in host execution. So it's not like in HIP, where when you use the triple chevron syntax or use the GGL function, that you would just enqueue an event for execution into the HIP stream, and then the host would just continue with whatever next statement it finds after that triple chevron syntax. But rather, in the OpenMP case, this is really a blocking operation where the host thread actually waits for the kernel to come back. We have a way to make this asynchronous, and I'll talk about that in a few minutes. The other thing that you'll notice is I didn't say anything about data movement. right? So if the GPU and the host CPU have discrete memory, so you have your regular host DRAM and some high bandwidth memory at the GPU, then obviously you need to move data around unless you have a system that is capable of this hardware support of memory coherency between the both memory domains. And so, what the OpenMP compiler is actually supposed to do is to actually look at the offload kernel, identify all the data that you're using, in this case, the array syntax in here, right? And it's going to find the definition of Y. And it will figure out that this is an array of that many elements. And so what the compiler then will do for you is basically add a map clause that says to from, so transfer Y with that many elements from the host CPU to the GPU memory, then run the kernel, and then bring the data back from the GPU, okay? So in total, next to the control flow transfer that I was mentioning before, we have the additional data flows of X, same thing as with Y. It's brought over before we launch the kernel, then we run the kernel, and then we bring both arrays back. The compiler will also do the same thing for scalars, except that it's treated like first private. So that means instead of bringing the A back, we just destroy the buffer that contained that scalar variable. And that's kind of a performance optimization and shortcut that we may have made in the OpenMP specification so that you can reduce the amount of map clauses that you write, and also acknowledging that in most cases, scalars in GPU kernels are either loop boundaries or are loop control variables, or are scalars that are used as, like in my particular example, as like a loop invariant thing, or even as a temporary that we don't have to bring back necessarily. Okay. The other observation that you may have is that copying X back is actually not really necessary, right? So here we see that X is read only on the GPU. It's only Y that we read and also modify. So that will have then a new state of the data in that array that we actually have to bring back. But we don't require OpenMP or OpenMP implementations to be smart enough to even figure that out, right? So if you don't say anything and the compiler figures that out, it's always a to-from transfer in both directions, before the kernel and after the kernel. And the one thing that I need to tell you, and I put it in quotation marks, is there a question? Nope. Okay. All right. The one thing that I did on this slide is I put the map clause in quotation marks because it's not actually a map clause that is kind of implicitly added. It's a presence check that basically transfers only if not yet allocated on the device. Okay. And we'll come back to that when we try to avoid data transfers and talk about that in a little more detail. Just accept it for now that it's as if you had added this clause yourself. All right, and then, if you're a Fortran person like I am, look at all the gray hair. So, the same thing happens essentially in Fortran, except for now curly braces, we have begin and end directive or block constructs. So the same thing happens when you augment the loop with target. That thing runs on the target device. The compiler figures out that Y is an array. It has these dimensions. So in this case, it's an assumed shape array. So it has this array descriptor underneath the array data, and so the compiler can actually look at the object that it has to transfer, read the array descriptor, figure out the shape of the object, the number of elements that it has to transfer, and which shape to reconstruct on the GPU, and it will perfectly do so. Now, one performance optimizations obviously is that X, we don't want to bring that back necessarily. That's one of the things that I would like to avoid to begin with. And so, let me now extend the Saxby example a little more, where now I'm more in line with what Saxby actually is. So now the data is actually coming in as flat pointers from the outside world, so from the call side. The size of the array is passed in as a size argument, and then the scalar is coming in as like as a float scalar. And now the compiler is no longer able to figure out what's going on, right? So in that case, now the compiler actually looks at this, right? It will figure out, okay, this is used as an array. It will look up the definition of Y, and it will figure out that it has to do this implicit array to pointer conversion. And regardless of what you pass in as an array, the compiler will not be able to figure it out, except if this is really a like a static size array or a variable length array, which unfortunately I think is still not part of the ISO C standard. So in that case, the compiler doesn't figure out what is the actual size behind that. It would still do the presence check, and we'll get back to that again later. But in that case, if you want to make this self-contained, you would have to map to the X and explicitly give the size argument. As I said, the compiler doesn't figure that out. And then the to from here for Y is also needed to describe to the compiler what is the size that it needs to transfer. Now, the thing is, the same happens in Fortran if you have assumed size arrays, which basically are the equivalent in Fortran 77 and later of passing in a pointer to the first element of the array, not having the array descriptors, as it's sometimes called, dope vector, and then the compiler will also not be able to look at the object to figure out what size is behind that assumed size array. And so in that case, you also have to manually map those things and tell the compiler what's going on. All right, and one thing that I didn't specifically prepare a slide for, because I went through a bunch of the materials yesterday and I saw that you've seen a whole bunch of OpenMP offload directives and recipes. So one thing that I need to tell you is that if I just do this, the loop execution on the GPU will be sequential. That's not by accident. This is actually intentional, because initially when we came up with the OpenMP offload model, obviously GPUs were one of the primary targets, but we wanted to make it generic enough so that you also could use DSPs, so digital signal processors with it, or something like a coprocessor that is built out of like 60-ish regular x86 cores, or if everything fails, something like a quantum computer that basically just calls, some quantum circuit instead of a loop. And so to make this happen, we kind of made the conscious decision to basically decouple management of data and control flow from actually creating parallelism on the target device. And so to make this fly on an AMD GPU, you would have to add pragma omp teams distribute parallel 4, or distribute a parallel do in Fortran to further parallelize that loop and use all the compute units, as well as fill up the wavefronts that we have available on the GPU. All right. Now let me talk about how you actually avoid data transfer and why is this necessary. I guess I'm preaching to the choir after like 3 days of GPU optimization topics. So the problem is this thing here. Right, this is something like PCI Express Gen 4. That's 27 gigabytes per second for MI100 and MI210. And there's this bottleneck from talking to a rather capable memory subsystem on the host system to a rather capable or very capable performing memory subsystem on the GPU. So on the host, we have hundreds of gigabytes per second. In the accelerator model, we have like terabytes a second memory bandwidth. And then in the middle, we have this slow bottleneck. So, we have to make sure that we're not crossing that PCI Express link too many times. So just to give you a number, 3 gigabytes roughly takes 1/10 of a second. So in the Saxby case, the GPU can run with infinite amount of memory bandwidth. In the end, you'll be performance of Saxby, if you do it the naive way, as I was showing on the previous slides, would just run with the effective bandwidth of 27 gigabytes per second, and actually half of it because we have to bring back the data again. It's actually 1/3 because you have 3 arrays that you transfer, 2 up, 1 down. All right, so optimized data transfers, how can this be done? And now comes in the presence check. Right, so this is now a little more sophisticated example. What I want to do is I have a whole bunch of data with data in and data out, and that should actually be A and B. And then we have a bunch of kernels that we want to run on the GPU, similar to what you would do in a HIP case, where you would run, the first kernel and then into a whole bunch of other kernels next to each other. so that you have this nice overlap between host execution and GPU execution. So think about this being, a mock-up of something like a parallel CG that you want to run, which consists of dot product, Saxbys, and matrix vector multiplications. So now let me look at the zeros kernel. So basically now I'm showing the full pragma set. So pragma ARM target teams distribute parallel 4, and the Saxby also have the same pragma. And as you can see, I now omitted the map clauses. All right, and what the compiler will now do is it will add this presence check for you, this map clause in quotation marks. And what I can do now is I can basically go in and say, OpenMP allocate a data environment on the GPU by allocating the temp array with n elements on the GPU space, transfer or upload A and B, and then take C back from the GPU when you're done. And what happens is when we execute this directive after this curly brace, so when the host thread is actually after this curly brace, shortly before it runs the zeros kernel, we have established the data environment, and all those variables have been allocated and transferred according to the specification. At the closing curly brace, which is actually this one, we will see that once the host thread reaches that point, it will automatically destroy the data environment and release all those buffers and also do the necessary transfers back if we asked for it. Okay. But the important thing is this just does a bunch of allocation, but it doesn't transfer control flow. Right? On the previous slides, I was using target directives to both send data and control flow and manage both aspects of the equation. And with that, with target data, I can take away the allocation and movement of data and from the actual kernel invocation. And so what happens now when the host thread makes this function call to zeros, it will go over to that one. It will pass in effectively the temp pointer. And the first time, the compiler will have added this presence check for A, and it will see that because it's a TMP pointer, it has been allocated before. So it finds an entry in a mapping table that describes to the system that TMP alias A in the zeros kernel has been pre-allocated, and we don't have to ship data again. Okay, then we can do the same with the compute kernels, and the Saxby now does the same thing. Essentially, now it has a presence check for Y and X, and it will figure out that X and Y are just aliases to the TMP and the B array, right? And it will not transfer the data again. It will just take whatever device buffer has been established by the target data environment. And so this is the effective way how you can decouple control flow from sending data all the time. And this now will run nice and fast because we don't do extensive data transfers except when we start everything, and in the end when we stop everything. Now the whole thing is still bound to the lexical scope of the curly braces, or in Fortran, the begin and end directive. But we also have a version of this that is called target ender data and target exit data, which basically resembles the notion of creating the data environment at the opening curly brace and closing it at the closing curly brace. And so now you can do things like having target ender data in a C++ constructor, allocate a GPU buffer that you need for that object to exist also on the GPU, and then in the destructor of the object, you just clean up by calling target exit data. All right, and I explained all this. This is the syntax. This is for reference. This is target update. So if you have this scenario where you establish a target data environment, you run one kernel, and for some reason you desire to update the input data or the input array on the host, then you can send a new copy. Consider this something like hip memcopy if you really wanted to move the updated input data over to the target device and upload a new copy to run that second kernel. All right, let me show you one slide about asynchronous offloading, and hopefully I'll get the point across that the OpenMP offload model is a very powerful model. Even though we made these decisions that I was explaining, the way you can do this to unblock the encountering thread is by unadding the no wait clause. And since I'm an OpenMP language lawyer, in OpenMP lingo, that makes the blue task, the red task, and the green task an OpenMP task. And they now run asynchronously with the host execution. So here's a purple task that is created by one of the threads, and it's likely running on a different OpenMP host thread. Then this first thread will encounter the blue target construct. It will fire off a kernel. It will then fire off the red kernel and the green kernel. Now, the thing is, in OpenMP, we don't specify, similar to what HIP would do, in which stream or how these kernels are being executed. So one implementation may actually choose to fire up those three kernels in the same HIP stream or underlying execution mechanism, which is then guaranteeing that blue, red, and green are running in order. Or another implementation may, even if it targets the same GPU, fire up all those kernels kind of concurrently to make better use of the GPU. So, we don't specify that in OpenMP at all. This is absolutely left to the implementation and an implementation detail and a quality of implementation issue. Now, how can you make sure that these guys are running in order? Because you can see that, this target basically produces some X that is needed by that kernel, and that red one produces a Y that is also needed by that kernel. And then there's this parallel or concurrent task that is actually initializing the A data, so the A array. And so we also need to make sure that the blue task does not start running before the purple task is actually run on the host. And the way this works is via task dependencies. So basically, OpenMP has a mechanism to describe ordering relationships between otherwise concurrent tasks. So here we can model that the purple task is creating a dependency. It's producing the A, so this is now the output or the source of the dependency. And then we can model that the blue task is waiting for that A to arrive, and it's producing the X. The red one, we can say, well, there's an input dependency that I'm not really showing how B is produced, but we can model that this task has this dependency. And then there's this output dependency for Y. And then the green one, it can have the proper input description so that OpenMP now knows that green may only run after both red and blue are done, and blue will not start until purple is done, or before purple is done. And by turning, let me finish one sentence, and I'll take the question. And the other thing is, because the OpenMP offload directives are considered regular OpenMP tasks, you can use even every other OpenMP tasking construct like task weight, task group, barriers, and whatnot to synchronize with both host CPU tasks and GPU tasks. Okay. Let me talk about hybrid programming, because that's probably what you're here for, and you want to see how you can nicely integrate it. So basically, in this case, I define hybrid programming as the interaction of OpenMP with a lower level programming model such as HIP, or for that matter, you could also think about OpenCL or some other programming model with 4 letters that I'm not going to name now. And what I'm showing is, here we have 3 interactions that OpenMP technically supports, out of which AMD, as of today, supports 2. So the first one is we can call low-level HIP kernels from OpenMP application code. That is, to me, the primary use case, because I'm a big fan of using high productivity models like OpenMP to get hopefully good enough performance. Good enough is in your hands and your definition. But if OpenMP does a satisfying job in terms of performance, there is no need to use some more low-level or lower-level programming model instead. So, my vision is that everything is just written in OpenMP, and for those cases where the OpenMP compiler doesn't do a good job, you would then have something like HIP available to use that as kind of a performance target. Okay. The other thing, to me, less relevant is we can also call OpenMP kernels from low-level application code, and that's actually the thing that I'm going to start with. And then finally, the third thing is in OpenMP, it's already being specified, but I'm not aware that anyone actually supports it. So there's a way how you can interact with the underlying asynchronous stream mechanism. So you can actually query the OpenMP runtime to give you the underlying stream object, return it to you so that you can use it to enqueue your own kernels and exploit additional mechanisms that are available via this low-level access to the machine. All right, I think you've seen this before. This is, SAXP again, where, I'm just allocating X, Y on the system, on the GPU. I'm including it or initializing it on the host, and then I'm doing a hip mem copy to move stuff over. Then I want to run or copy the result back and free the GPU buffer. So pretty much the same thing. And I guess that slide also gets across that you get this additional productivity by OpenMP by not having to write those hip mem copies yourself, but rather OpenMP figures them out for you. All right, and then we deallocate the buffers on the target GPU. And what I want to do is, in that context, I have an existing implementation of SAXP that I was showing before. And now the question is, how can I invoke that thing here from this context, right? If I pass in the device pointers and for X and Y and pass in some scalars, how can I make use of an OpenMP directive to parallelize that instead of writing that as a hip kernel? Okay, so what we need to do is somehow we need to convince OpenMP to access the raw device pointers and not attempt the presence check, because it will not find the XDEF and the YDEF somewhere in some internal table bird in the OpenMP runtime, but rather we need to somehow tell OpenMP that what is coming in here are already kind of useful device pointers, so bit patterns that you can just dereference and they have a particular meaning on the GPU. So this is how it works. Hip pointer translation actually works by tapping the programmer's brain. So you have a convention, at least I do, where X is the host pointer and X_def is the corresponding object, but now the device version of that. And then in my brain, I'm connecting X and X_def via the hip memcopy API that requires both as an argument. So if you do the hip malloc for XDEF, you get this buffer. Then you do the programmer brain logic basically associates that whatever is in X, say it's ABCD, is the same object as X_def, just the host version of it. And then you write the corresponding hip mem copy that basically takes this association in your convention and in your brain to implement the proper data transfer. And that's what OpenMP basically does for you automatically. So now we need to tell OpenMP that you're actually passing this thing, the EF12, instead of a real host pointer that OpenMP would expect otherwise. And the way you can do this is via an additional clause that you can add to the target directive. It's called isDevicePDR, which basically tells OpenMP to just copy over, regardless of what is in X and Y, take the bit pattern, ship it to the GPU, and start dereferencing it as a data pointer. And if you didn't lie to OpenMP, and that's actually a device pointer, then this thing will actually compute the SAXP between X and Y. Okay. This also removes the presence check for X and Y. And you still see that A and N, the regular scalars, are still transported over using a map2 clause. So it's still kind of mixing direct pointer access and using presence check or automatically added map clauses under the hood. Okay, so that was the first case. Let me show you the second case. This is calling hip from OpenMP offload regions. So here's what I want to do, right? So I have some target map thing going. I initialize the data. I send it over to the GPU once more. And then I'm calling SAXP. Okay. So basically now I have allocated X and Y both on the CPU, the original host version, and the GPU version for Y in the GPU thing. And let's assume that the compiler doesn't do a great job for SAXP, and it's not giving you the expected performance for that kernel using the regular, presence check and everything that you use. Okay. So let's assume that we now want to use Saxby, or we want to implement Saxby in a low language like HIP. Okay, so here's the corresponding kernel. I guess you've seen this quite extensively in the past. I don't want to do anything fancy, so the first thing is, it's a plain naive parallelization of the Saxby kernel as a global kernel using the thread IDX block IDX thing, the usual pattern. Then I'm describing, the Saxby operation for that single point in the work grid, and then, to make my life a little easier and avoid some if conditions or additional padding or whatnot, I just assert that, n is a multiple of 256, which is the block size that I chose for that example. Okay, and then, triple chevron syntax as usual. Now, the thing is, Saxby HIP here, the X and Y, those actually need to be device pointers. And I probably should have called them X_def to get that point across, that these pointers are actual device pointers going forward, right? So if I pass in the host pointer like I would do in an OpenMP kernel to exploit the fact that there's this presence check and this automatic mapping being done, then the HIP kernel will fail with an access violation because the host pointer doesn't make any sense on the device as a device pointer without the translation. Okay, so these are device pointers, and we somehow need to get them out of the OpenMP runtime system so that we can say, whatever X is, give me the X device version of that, and so that we can pass that along to the kernel. All right, so pointer translation in OpenMP. So when you create a device data environment, OpenMP actually creates a mapping between the actual memory pointer on the host and the memory pointer on the target device. And I put virtual in parentheses because actually, depending on the GPU implementation, on x86, this is definitely a virtual pointer that is undergoing memory or pointer translation via the memory management unit, and it's going to be translated into a physical memory pointer. And on the GPU, whatever the GPU implementation needs. So it could be a virtual memory pointer or it could be a physical memory pointer. And then, this mapping is automatically created. So when you do the target map or target data map, then you will find an entry in this table. So when you write something like this, there's a device pointer that is being allocated with enough memory behind it. Again, let me call it EF12. The original host pointer is ABCD again. And when you do this map to, what OpenMP remembers in its internal mapping table, it will remember that X, if it's used as a host pointer, has that value. And if X is used in the context where a device pointer is needed, so that means inside a kernel, like in the Saxby kernel, then it needs to have this value, right? And when you then run and execute at runtime, the presence check actually looks up the host pointer, it'll find it, and if it finds it, it will translate the X and replace it with the device version of X and ship that pointer over to the GPU kernel. Okay, so this number, this EF12, that's exactly what we need to make that happen on the GPU in terms of HIP kernel. Okay, so let me show you a bit of example how this works. And there's a little bit of a brain twister, and I happily admit that this is the case. So say you have X being initialized to ABCD to, malloc, whatever. And then when you use target data, use device PDRX. So this now does the pointer translation that I was showing on the previous slide. You actually get a shadowing X inside those curly braces, right? Outside those curly braces, even though we're still executing on the host, X is now a pointer that is pointing to device memory. And you can think of this as now having two X's, the original X that is valid in that context. It is valid in the context outside after that curly brace, but inside those curly braces, there's an additional X, which basically completely hides that X, and this hiding X basically now is the device pointer that you can ship to a HIP kernel. All right, let's put this together. So, my thing becomes slightly more complicated. So I'm creating the target data here, and let's assume, I'm showing the mapping table for X and for X in this case. So outside here, X has the value ABCD. When we run compute 1 and compute 2 on the host, it still has X ABCD. But since we now did the target data map here, OpenMP now has this internal mapping table, which basically contains the information that X has as a host version, ABCD, and the device version of X is EF12. Okay, but X is still pointing to the host memory because we're still running in a host context. Then I do the target update as before, so nothing fancy going on here. And then I want to call the Saxby HIP kernel down here. And now I need to make this host pointer to device pointer translation. So I have another nested target data construct, which basically has a use device pointer clause that I was showing earlier for X and Y. And what now the mapping table contains, we're still executing on the host, is X still has the same host value, but it has the same device value. But now X is shadowing the original definition of X, and it has been replaced by what I was calling X_def in my earlier example. Okay, and now I can call Saxby HIP and run that thing in the context of HIP. And these things will just work because it's now a bit pattern that HIP can use and exploit to dereference data in its kernels. Okay, regarding implementation status, the two things that I described actually work. So you can call a HIP kernel with OpenMP managed buffers like I was showing with use device PDR. And you can call an OpenMP kernel with HIP managed buffers via is device PDR. That also works. And I just tested it like 2 weeks ago and it was still working. The only thing that we don't support yet is the coexistence of HIP and OpenMP kernels in the same translation unit. So if you want to do these tricks that I was showing, you will actually have to have one source file that contains all your HIP invocations and your HIP API stuff, and then have another OpenMP translation unit where you gather all your OpenMP code. You have to feed the HIP code via the HipCC compiler, and the other code needs to go through the AMD Clang compiler that we ship with ROCm, and then you can link everything together, and it's supposed to work. All right. Okay, then final topic, integrating asynchronous programming models. All right, let's assume, and you've seen one in the past 3 days, HIP. HIP, stream-based offloading, is inherently asynchronous. So if you use HIP memcopy, obviously it's not. But if you use it properly with HIP memcopy async and the triple chevron synchronous syntax, then you can actually continue on the host thread and fire up events in the HIP stream that are then processed in order by the HIP API. There's a question in the chat: is it possible to get the presentation? Yes, I think I have seen it on the workshop slide or the workshop site. It is day 4, slides and exercises for today. One thing that I did overnight was I added like 3 more slides or so. So I'm going to share with George an updated version so that you get also what I was presenting here. Now, obviously, we'll also fix a bunch of those nasty typos that I still had in there. Okay, so HipStream is one primary example of this. But there's also MPI who has asynchronous send and receive, right? Or there are libraries where you can do asynchronous I/O. Or in general, there may be programming models or APIs that you want to marry your OpenMP code with that executes asynchronously with the host threading and the host tasking. All right, let's, as an AMD UI, let's stay with HIP. So let's do something like this, right? Do something really important on the host, then do a HIP memcopy async to bring some data back from the GPU, then do something else that I consider important to be done. And then before this, do other important stuff that is actually using the GPU data. I want to do this HIP stream synchronize so that, this hip memcopy async hopefully completes right with that thing happening, and so we don't have a nice overlap between data transfers and CPU computing. But let's also assume that these things are also things that I would like to run, at least to the extent possible, in parallel using my host threads. So the question is, how can we marry this asynchronous world coming in from the GPU via HIP, and how can we marry that to the asynchronous API that is coming from the OpenMP world, right? So somehow we need to make those two things wedge. All right, let me try this. And I'm going to make this interactive just as a warning, okay? So here, I'm creating task A, which does something, then enqueues the hip memcopy async, then task B does something else, assuming that those two things can really happen in parallel. And then I have task C, which does the hip stream synchronize and do other important stuff. Question to the audience, will that work or will it not work? You can type your thoughts into the Zoom chat if you don't mind. So there's a cross which I interpret as no, that's not going to work. Okay, what else? Bring it on. Bring your thoughts, please. Let's make it a little bigger so that I can see everyone. No. Okay. Anyone attempting to explain why it's not going to work? I'll take 2 answers as a sufficient amount of reply and interactivity. Anyone? Well, there's a really, really bad race condition. Okay. So let's say thread A is going through hip example. It will create task A, it will create task B, and then create task C. Okay. What will now happen is if you have more than 4, well, more than if you have, say, 4 threads available, or even 3, it works. Right. So one thread is going to grab task A, start executing, do something. Some other thread will start executing task C. It will immediately enqueue the hip stream synchronize. The hip stream synchronize will look at the hip stream and say, all right, there's nothing to synchronize with, I'm done, and immediately return, and the code will start do other important stuff. In the meantime, the task A thread probably has completed do something, and it will start this asynchronous memory copy, which basically now happens unsynchronized because the hip stream is long gone. The synchronization operation is long through. But also, there's a good chance that this memcopy async will just destroy what this guy is working on. Right? So you will not only work on outdated data, you will probably see anything in between from, the first half being overwritten by the memcopy async and the other half still being processed by PCI Express. That's nothing you want, right? So that's a really bad race condition. And also, in theory, task C may also start execution before task A is even considered for execution, depending on how the task pool is implemented in OpenMP. And it's perfectly fine to do this because there are no task dependencies. All right, question, how can we fix this? It's actually dependencies. I should know my slides. All right, okay, let's put in a dependency. On the stream object, I could also use DST, but for general confusion, I'm just showing, this task is somewhat modifying the hip stream, so we can also use that as a dependency arc. And then we have the corresponding input dependency in task C, right? Which basically means now task A will start execution, and task C will not be scheduled for execution until task A has actually completed, which guarantees to us that the hip memcopy async is now enqueued. And so when this task A finishes, the memcopy async is in the queue, and hip stream synchronize will actually find something that it can synchronize with. Or if it doesn't find anything anymore, then the memcopy operation was quick. So how does that work? Well, it actually does work. But the problem with that solution is that you actually lose an OpenMP thread on the host while you're waiting for the hipstream synchronize. So you NQA, and let's assume the hip mem copy really takes a long time, like 2 seconds or something. So in that case, this task C will be in the stream synchronize until the 2 seconds are over. And in those 2 seconds, the executing thread that scheduled task C for execution will continue spin waiting in the hip stream synchronize. Now, if you have a nice parallel Genoa system with like 192 threads, you can probably spare 1 or 2 threads, right? But if you have a whole bunch of kernels going, or hip kernels, or whatever you do asynchronously, you can actually take out OpenMP thread after OpenMP thread. Eventually, they will return to the computation once the synchronization is done. But in the meantime, they're not doing any other useful work that you may have created in terms of other OpenMP tasks or other OpenMP constructs. All right, so that's a problem, and we want to get away with that. All right, so the solution in OpenMP 5 is detachable tasks, and I tried that, I think, last week with the AOM compiler, and it actually worked there. So the official name is detachable tasks. I'm going to call them zombie tasks. So basically, if you think about a state transition of an OpenMP task, and I don't want to go into sufficient detail, and every 5 years, we have a discussion in the OpenMP language committee if we should come up with a state diagram for OpenMP threads and tasks. And anytime we do this, somebody says, this is wrong, this doesn't work with our implementation. So anyway, so we don't have that. But for the sake of explaining this feature, let's assume there's a state transition that when a task is being created, it's waiting in a waiting state in the task pool. And that waiting state transitions to executing once an OpenMP thread looks at the task pool, grabs the task out of the pool, and starts executing it, and actually does useful work of the task region. And then at the closing curly brace, so when the task is finished, it transitions from executing to completed, which basically means that task waits waiting for this task groups waiting for the tasks, or sinks of dependencies where this task was kind of the source, will see that this task has been completed and will continue execution because they now have this satisfied, or when all the waiting relationships have been completed and are satisfied, they will continue, and that task will make its contribution when that happens and when it is considered completed. And then it's also gone from the system. Task descriptors are being released, and everything that the task was about has been released and given back to the OpenMP runtime system. So what we can now do is, with OpenMP 5 and those detachable tasks, we can make those tasks a zombie task. So right in the middle of the state transition, where it stops execution, but before it is considered completed, we store the task in a variable. We just grab it out of the system and we stop it from completion, right? That means now every task that is waiting for this zombie task will not have a chance to start executing because the task is not completed, and so dependencies are not being fulfilled. The task wait has one outstanding task that it's waiting for. So that basically blocks dependencies from being processed after the lifetime of the task. And so what we can do is there's an OpenMP event handle T that basically grabs the task and stores it in that variable. We have a detached task clause that basically implements this intersection between going from executing to completed, grabs the task and stores it in that variable. And then have a runtime API that basically lets you grab whatever task is stored in that handle variable and tell the OpenMP runtime system that it's now being completed. If that doesn't make no sense, here's an example. So let's say you have a task that has this detach and has a corresponding event handle T variable. and it's executing some arbitrary code that we don't particularly care about at this point. So at the closing curly brace, this task stops execution. The worker thread becomes available for other tasks, but instead of being completed, the task is stored as a handle in that variable up here. Okay, so that thing now contains basically this task. And the runtime system, the OpenMP programming model, still sees this task as not completed, which basically means that this task wait down here has to wait for exactly one child task. The current count of completed tasks is 0. That detached task did not complete, it's stored in the variable. So the task wait will not continue execution and let the thread that is blocked in there continue with more work. Then somewhere else, in another OpenMP thread, in another OpenMP task, we're calling OpenMP fulfill event, passing in this handle to the task, which basically now means that OpenMP considers that task to be completed. It destroys it from the system. The task wait down here will be notified that now one task has been completed. The waiting goal is 1, and so the task wait will continue with execution and let the block thread continue with whatever it's supposed to do. All right, let's put all this together in a bit of code. So what I'm doing here is I'm adding a HIP event up here, right? I do a detach on task A, and the HIP stream synchronize is actually gone from the code. Instead, what I'm doing right after HIP memcopy async, I'm adding a HIP stream add callback, which will be executed once the async memcopy is completed. So that's a new event in the stream, and due to the in-order nature that I'm exploiting here, I'm sure that when the callback is triggered, that the memcopy operation has been completed. All right, so what happens now? Task A detaches. Oh, task C is after a task wait. This task wait has the waiting goal of 2. Once we schedule task A, it starts executing. Once we schedule task B, that task starts executing. It finishes at some point. The count is reduced to 1, right? So task wait will now wait for 1 outstanding task out of 2. But that task, as I said, will not complete automatically because it's going to be trapped in this variable and stored in there, being stopped from completing. So that means the task wait down here will wait until my left index finger will go away. So at some point, the HIP memcopy operation will be done, right? So that means HIP is going to invoke this callback, and the code for this callback is shown up here. So basically, it will now call OpenMP fulfill event. And since we passed in a HIP event pointer or a pointer to that variable, we have to do some C pointer conversion weirdness to get to something that we can actually pass into OpenMP fulfill event. But basically, we take the callback data, which is a pointer to the event handle, we convert that to the right data type, we dereference it once so that we can pass it to the function. And then we call OpenMP fulfill event. And in that moment, we call this function. The task is being completed. My index finger goes away. The remaining waiting tasks become 0, and the task wait becomes permissible. And task C is being scheduled for execution. And with that, I did not lose an OpenMP thread. Right? This is all standard OpenMP tasking mechanism, which are geared towards keeping OpenMP threads as busy as we can make it. No thread is being lost to some sort of waiting relationship. All right, we can also do it with task waits if you really want. So in this case, I'm now using the proper DST variable, so the destination variable. The code is actually the same, and I'm just going to run through it once more real quick. So again, down here, the task will detach. This task down here is actually scheduled or waiting in the task pool, waiting for its input dependency to be satisfied. It will not execute because the input dependency satisfied by completing that task A, when the callback is added or executed at runtime, the fulfill event kicks in. It will mark task A as being completed, which in turn tells OpenMP that for this task C, all the input dependencies have been satisfied, and task C starts execution. All right, I'm already at the full hour, so just a bunch of things real quick. So, 1 hour is not enough to talk about OpenMP in all its glory. I just came back from a 3-day OpenMP tutorial in the context of Price at LRC, where we started OpenMP from scratch, including host threading, and ended with GPU programming and how it integrates with host threading. And I could talk like a day or maybe 2 days about all the specific aspects of GPU offload programming with OpenMP. But anyways, it's a major offload model with support for asynchronous offload and data transfer. So we have all that you know from HIP. The benefit that I see with OpenMP is that it nicely and tightly integrates with the OpenMP multithreading on the host. So you've seen that it nicely integrates with task dependencies and all the synchronization mechanisms that we have in OpenMP. So you don't have to mess around with, HIP signals and HIP events, and probably not those callbacks that I was showing. You can use OpenMP high-level synchronization mechanisms for most part. What I didn't cover here are the more advanced features. So there's a whole management API that lets you deal with memory management on the GPU device, including memcopy operations and rectangular memcopies. I'm not showing those. The pragmas are already quite powerful, but you can use that for libraries. And if you feel that the OpenMP directives are not sufficient, you can also use the underlying APIs if you really want it. I didn't show interoperability with native streaming interfaces because we don't support that yet, but support will be coming. I think the client community is really working on that. And what I didn't show either is unified shared memory support. Just rest assured that it's there. There's a directive where you can declare that your code needs that, and then you can strip out the OpenMP map clauses. Well, you don't necessarily need them anymore. They are then used as a performance optimization. The presence check are mostly gone, and you get, let the hardware take care of memory coherency instead. All right, with that, if there are any questions, legal disclaimer just for the recording, and then the AMD logo, and thanks for listening. So question 1, any general advice what to do with present statements in OpenACC when porting OpenMP plus OpenACC to OpenMP? OpenMP actually has an equivalent of map press or the present clause. So it's a mere thing of translating the present clause to the corresponding map clause, and then it's basically done. So that's not much of an overhead. The real trouble starts when your code actually uses something like OpenACC kernels, which at the moment there is no equivalent in OpenMP. But we are hoping that OpenMP 6 will have a similar feature than as the kernel directive in OpenACC. And so we're kind of trying to match there as well. Okay, so question 1 should not be a big deal. If you want to shoot me an email about this, I can actually dig up the exact translation. Okay, let me take care of question 2 in the chat real quick. What should we do with data types defined in HIP, like float2, when we are not allowed to use them in our OpenMP file? Seems to be necessary when using HIP FFT with data created with OpenMP. Okay, that is that's a very good question. I would assume that you can get away with treating 2 float2s as like a 4-byte integer. And then, you will have to do a hack because the float2 is actually a HIP extension. And it's not a ISO C++ or ISO C extension or data type. And so, because OpenMP is only defined on top of ISO C and ISO C++, as well as ISO Fortran to varying language levels, you will have to do some sort of hack to make that work. And the best I can come up with at the moment is that you just treat the float 2 as like, you know, an opaque data type, where you just have like, you know, either void pointer or character pointer to it, deal with the presence map and everything as part of the character pointer. And then once you transition to HIP, unpack it like I was showing with the HIP event handle T, and then do basically a reinterpret cast on the data type to convert it back to float 2. So the unfortunate thing really here is that it's not an ISO data type. Put it this way, because HIP is meant to be a programming model that directly matches AMD GPUs, similar to what the 4-letter API is for the other GPU brand. You can naturally do things in that model that we cannot necessarily do in OpenMP, because either we would break portability in OpenMP by allowing these kind of things, or we cannot really exploit like the float 2 thing that that was asked for, because it's not part of the base language that we support. Okay, but from a technical standpoint, right? If you write a nice data parallel HIP kernel, like the Saxby one, right? I don't see why OpenMP should actually be a lot slower than HIP. Probably not 100% match, but I would, you know, my goal is that we get OpenMP implementations at various companies, not restricted to AMD, by the way, and it's my OpenMP hat on for that reply, or for that answer, that you get reasonably close, like, you know, 80%, 90% of native performance, so that, you know, you can basically accept the smaller performance penalty in favor of being more productive, and then have this, you know, this path towards HIP or the lower level programming models, so that for those cases where you really want to close up to HIP performance, you can do this via this transitioning that I was showing in my slides, and how you can transition from OpenMP to actual HIP execution. Now, one thing, and let me word this carefully. Obviously, you know, our compiler performance still needs to be improved, right? So some of the performance issues that you may be seeing with OpenMP code on AMD GPUs may actually come more from the fact that our compiler still needs to mature, rather than, you know, OpenMP being the culprit, or the OpenMP that you're writing being the culprit. Okay, so this is why these kind of workshops are really relevant for us, because these give us a data point to work with our compiler team at AMD to figure out where these performance bottlenecks come from. If they're coming from OpenMP implementation side of things, then obviously we are up to fixing it. If they are coming from the OpenMP side of things, like, for instance, OpenMP as of today does not really support LDS storage, right? Or shared memory in 4-letter terms. So, you know, that is something that we would then have to work on as part of our engagement with the OpenMP language committee, to bring OpenMP forward to have, like, you know, hardware agnostic features that would allow an implementation to map it to the best possible use of, say, if I may stick with that example, of the GPU memory hierarchy. And for instance, the Clang folks are actually working on figuring out if you have like a certain nesting of data in your kernel, that they can actually add the __ shared in front of an array and put it into LTS automatically. And, you know, since we're piggybacking on what the Clang community is doing with our compilers, eventually that will merge in our compiler, and in turn we are giving back to the community some of the performance optimizations that we're doing for our GPUs, and the Clang community can use that and you know, to improve the standard Clang as well. Yeah,
So,
so in OpenMP, you can actually, as of today, already use target teams loop instead of ACC parallel loop. So we do have the loop construct. Thing is, implementations don't yet support it fully. They recognize the syntax, but the implementation needs to mature and needs to be improved so that it actually delivers performance. But that's being worked on by the community as well as AMD and other companies as we speak.
so I tried to answer this one about ACC parallel loop, default, private, present. I don't see any value in keeping the default or the private or the shared in GPU pragma. Do you have any thoughts on that?
Yeah, default none is a safety mechanism in both in OpenACC and OpenMP. So basically, it tells the compiler that it shouldn't do any implicit data sharing, like making stuff shared when it's defined outside the parallel region, and that you have to explicitly name all the data elements that you want to work on. It's a matter of style. OpenMP has it also. It has it also for target teams, distribute, parallel, do, and so forth. So you can add it, but it means that you will have to, be explicit about private and shared. And then the present basically translates to an OpenMP clause that basically is defined in the context of map. I didn't specifically show it in my slides, but there's an equivalent of that. And as I said, if that person would love to send me an email as a quick reminder, I can also update the HackMD and add the solution to it.
Right, but what would private and shared do in the GPU context? Because the data model is different on the GPU than the CPU.
So shared would do the same thing as on the host. It would share across all GPU teams and threads. Private would instantiate the corresponding list item. So if it was private X, then each GPU thread would receive a private X. It's basically
So in the register, it would create a register for it?
Yeah, something like that. Or, split it into the GPU stack if it runs out of registers.
There's questions about the level of support in Fortran on Lumi. And I guess it's on any of the Fortran OpenMP compilers. I do have a page there for Clang. I don't know of any site that says what is supported for Flang. Can you maybe?
Well, which Flang are you talking about?
AOMP, I would assume.
So there, it actually works. So that's why I said, these are supported things, and I keep testing it. Same for use device adder, by the way, which is another variant of the use device PDR. It would take me like 5 minutes to explain the actual differences between the two, but both are supported. And if you give me like a quick second, I can look at the Cray slides that HPE has been presenting at supercomputing in the OpenMP buff, and probably has the information about the level of support for use _ device PDR. So according to these slides, CCE 11, November 2022, so quite dated already, should support use device adder. They don't explicitly list use device PDR. But given that it's a 5.0 feature, they, I think, support the OpenMP 5.0 definition of that feature. I'm 99% certain about this.
And do you have any knowledge of G4tran that's in either Siemens or GCC?
Actually, I don't, but I can find out.
Do you have a site which has what is actually supported with the Fortran?
Well, what I have, or what I can point folks to, and it'll end up in the chat in like a second. Is this page. So it basically lists all the implementations that we know of, including tools. And we basically have asked the OpenMP members in the OpenMP ARB to give us the most recent update, and all the pages contains for each implementation a read more link, where hopefully you can find more about what is actually being supported. And then when you go to the Clang pages, it basically, at least for Clang, has this. So this is now where Clang supports OpenMP. And I'm not sure if they still maintain the same kind of page for Flang, because they now abandoned the old PGI front end pretty much, and based everything on Flang LLVM, which used to be called F18. And that one is much less mature. But I don't see much of the same page where it would list, individual OpenMP features. But I know that they're working on all this, and they are, I think they're now at OpenMP 2.0 or 2.5. They're not working in strict historic order, so you may actually see that it supports GPUs before it actually supports like other OpenMP3 features.
That's really helpful. Who asked this question? Do you have more? Is this answer what you wanted? Okay, if Michael, if you get a chance, if you could maybe elaborate on the private and shared, that'd be helpful.
Okay.
How that affects GPUs, because I don't quite see where that would be significant for GPU programming.
Yeah, I mean, I guess shared and private is more about, especially in Fortran, where you can only declare things in the specification part of the subroutine. You will have issues with, like, okay, here's a loop variable J that is declared right up from the procedure, and you got to do this and make this a private variable so that the outer I loop is parallelized across the GPU, and the J loop runs in a decent manner without missing iterations or duplicating iterations. So that's, I think, where it becomes in handy. It doesn't have, at least in the OpenMP sense, have a particular meaning in the sense of that the compiler would actually exploit it as, if it's first private, it should go to, say, shared memory or LDS.
Yeah,
it basically has the exact same meaning for GPUs as it would have in the context of host threading.
Yeah, and I think some of our participants are more familiar with the CPU and shared, and unfortunately that term means something different in the GPU world, shared or local, depending on the vendor.
Well, it does in
that
OpenMP.
memory.
It does not in OpenMP, right?
Right. So they have the overloaded meanings.
Yeah, that's probably a fair statement. Yeah.
Um,
OpenACC is a different language, so even if things are having the same syntax token, it doesn't necessarily mean that it's the same concept. So example from general computer science for the C++ folks, a C++ reference is not a Java reference. Both are called reference, but they're completely different concepts. And it's the same with OpenACC and OpenMP.
So you mentioned a little bit about LDS, which is sort of the programmable cache on the GPU.
Yes.
There's some new constructs in OpenMP with memory space types. Does that help with that LDS storage, or is that
eventually that's meant to address exactly that problem? Yes. So as I said, if you have certain nesting for certain kernel types, Johannes Dörfert at Livermore, who's pretty much the lead of the OpenMP implementation in Clang, has shown that they can infer using LDS for these kind of specially nested data types or variables. But that is a specific programming idiom that you would have to adhere to. And that's kind of, an implementation. Another implementation will probably not figure that out and not do it. With OpenMP memory spaces, we intend to have the right kind of syntax so that you can express to the implementation that should something like LDS be available, that it should use Teams local storage in OpenMP terms, and an implementation would then figure out if teams are mapped to wavefronts, then that team local storage should be the equivalent of an LDS allocation.
Okay, we have question 2 here, which I think you answered, and I don't know who answered it here, but I think there was a posting earlier in our earlier OpenMP session, which basically gave that same syntax that you mentioned verbally. So I think is that correct? I'm asking whoever answered here.
Okay, well,
must have lost that one.
Okay. So, and then the other one, can we create streams for GPU with OpenMP offloading without using HIP? Yes and no. No, in the sense that OpenMP doesn't say anything about how the GPU kernels are actually being executed. It will require, well, it does not necessarily, so our OpenMP implementation is not even based on HIP. All right. So, it uses some different concept underneath. And so, it does not necessarily have to use something like a stream object to actually implement GPU offloading. It doesn't even have to fire up, the traditional compilation chain that you would find in HIP. It could basically just, directly spit out low-level assembly code and everything, and directly target the GPU via the driver. We do base our implementation on some low-level runtimes of ROCm. And so, OpenMP does not have this mechanism of a stream. We talked about this, but that would already prescribe a particular implementation strategy under the hood, and we wanted to avoid that. What you can do, however, and that's the yes part of the question, there's a feature called interop, which basically gives you a way to query implementation-dependent low-level information. And for OpenMP implementations that are actually based on a stream concept, you can get that stream object out of the low-level runtime interfaces and return it to you as kind of a raw pointer. And then, but you're obviously then out of the OpenMP specification, you're then in implementation-defined land. And then you would have to understand that, I don't know, that the void pointer that we return as part of the interop query, that is actually a stream object and which data type to cast it on and what interfaces you would have to use with that stream object. And OpenMP doesn't take it back anymore. All right, that's also a feature that we're working on OpenMP 6 to basically then have OpenMP take a stream object. If you have one and OpenMP can support it, or the OpenMP implementation can support it, you can basically then hand over the stream object of your underlying GPU implementation and tell OpenMP, hey, use that for kernel invocation. We did the reading part, and we hope to have the setting part done in the time frame of OpenMP 6.
So say maybe future.
Yes.
Does the dependency features don't really mimic streams then?
No, they don't have to.
Okay,
so
interesting.
They can use some underlying graph API if they really wanted to. They could be implemented using, HIP event data types and stream events. Or, as I was sketching, they could be implemented using the regular OpenMP tasking mechanism, and just sit in the OpenMP task pool. So that's, and that's exactly why we don't specify that in OpenMP, because we want to give an implementation to come up with the smartest possible implementation without confining them into a particular solution space, and accidentally prescribe an actual implementation. We already have way too many places in the OpenMP spec where this happened by accident, and we do our best to avoid them in the future. There's a question appearing.
Oh, yes.
How does the GPU maximum number of concurrent different kernels map to OpenMP limits? Okay, that question is a little hard to parse, but let me attempt my best to answer it. So OpenMP does not per se have a defined limit for these, either the number of kernels or the number of different work sharing tasks. Of course, infinity is not an option for an OpenMP runtime. So what you can assume, let me explain it for OpenMP tasking, that OpenMP has a certain limit of how many tasks it can have pending in the system and executing. So obviously the number of tasks being executed at the same time is defined by the number of OpenMP threads that you have available. And usually that number is defined by the number of cores that you have in the system. If you create like a gazillion of tasks, OpenMP will naturally have some sort of implementation limit, at which point it will stop storing more tasks into the task pool, but rather either hold task creation. So, it basically stops from creating a new task and starts scheduling tasks instead, and then continues with task execution or creation of new tasks and scheduling new tasks when a lower threshold is reached. Or what's always possible is, because in OpenMP tasking, we describe OpenMP tasks to be concurrent units of work which can run in parallel with another OpenMP unit of work. It may execute in parallel. It does not have to. So another valid implementation of that would be if all the task pools are full and everybody is busy executing tasks, then if you want to create a new task, you actually don't create it. You just execute it right where it is in the encountering thread, and you don't even bother with creating a task in the task pool. That's another sufficiently correct implementation. For GPUs, we have the same thing. Right? Even though you, as a programmer, you express your desire to run an OpenMP offload task on a GPU, with no wait and you want that to be asynchronous, OpenMP can choose to not honor the no wait clause at all and just execute that GPU task right where it is in a blocking fashion. That's absolutely permitted by OpenMP. And so we can get away with not defining these limits, but rather just say, you know, this is potential asynchronity. And if you exceed the natural limit of the underlying implementation, say, you know, the number of events that you can have in a HIP stream or in the underlying stream, or in the total amount of work that you can schedule via these streams across all the available GPUs, then OpenMP may actually make an internal decision to basically implement a GPU kernel in a blocking fashion until the streams clear up sufficiently, if they use streams. Okay, and you know, having executing those 3 kernels that I showed right after each other sequentially in a blocking fashion would still be a valid implementation of the data dependencies that I was describing in the task dependency graph. Okay, so there's like, you know, we have enough backdoors in OpenMP so that we have enough may run concurrently, may run in parallel, so that an implementation shortly before it's overloaded and would be crashing the system or, you know, oversubscribing the system too much could take a step back, let the system recover, and then start pushing work again. All right, and then finally, the other thing is in terms of the concurrency exposed on a particular GPU kernel itself, like the Saxby kernel, how parallel does it run? If we don't specify anything, the number of teams that OpenMP creates and the number of threads within a team are implementation defined. So actually, your implementation should tell you what is the default. And then you can override that by saying, all right, you know, like I did in the HIP Saxby kernel, I want the block size to be 256. And in OpenMP, you would define a corresponding thread limit, which would then give an upper bound to the implementation of how many threads it should create per team. And then it depends, obviously, on the number of loop iterations that you have. If you ask for more parallelism, then you can generate using your N in Saxby, then obviously the limits will be lower. But again, OpenMP has the freedom to basically make a decision about what these limits are, unless you explicitly ask for them, and then typically the limit is an upper bound as well. I hope that answers the question.
Okay, I'm just gonna introduce myself and then I'm gonna turn off the camera so I can save some bandwidth across the ocean. Hello, everyone. My name is Alessandro Vanfarillo. I work in the Frontier Center of Excellence here at AMD. So I do a lot of user support and application optimization for Oak Ridge National Lab, but I work in the same group as George and Bob, and we all collaborate on also other projects like Lumi or KTH and other problem like that, other project like that. It's a little early for me, so if I'm not super sharp, I apologize, but it should get better over time while the coffee kicks in. The presentation is going to be, in terms of slide, pretty short. It's going to be a very, very practical presentation. Lots of demo of mostly TensorFlow and PyTorch. I don't mind being interrupted, so if you have questions, just say something and I'll answer right away. You don't have to wait for an interval or the end of the presentation. Okay. That being said, I think I can start sharing my screen. All right. So yeah, Alessandro Vanfarillo, Frontier Center of Excellence. We're going to talk about some ML frameworks. You don't need to see this, but I have to show it to you. And this is the agenda. So I'm going to show you a few details between the two main architectures that we're targeting nowadays, like CDNA, CDNA2. What's the main difference between the two, and why you care about this in ML, in the ML environment. Very basic introduction to a little jargon. What is machine learning? What is deep learning? What is AI? And just to clarify, it's one slide, I promise. Demo on TensorFlow, demo on PyTorch. That's it. Let's start with the CDNA and CDNA2 architectures. So here's just a roadmap of where we're going, where we are headed in terms of data center accelerators, because they're not even GPUs, since they don't have even a video port anymore. But 2020 we had the CDNA 1 or CDNA, which was the MI100, still good GPU. But next, for really target the HPC and ML market, we created the CDNA 2, which is what you will have on Lumi, for example. This was released in 2021, second half of 2021. And it was based, it is based on a 6 nanometer technology. And you will see what I mean in another slide. We are currently working, and we are very excited about the third generation of CDNA called CDNA 3, and it's also called MI300, which will be for certain customers an APU, which we are extremely excited about it. And then CDNA 4 will be something else in 2025, which still we cannot disclose yet. What are the difference between the two, and why do you care? So this is MI100, a pretty powerful card. You can do a lot of computation for single precision, 256 operation per clock per compute unit. And for MI250X, which is what you have on Lumi, for example, you have 110 compute units. This I think was 120, but this is for GCD. So for an MI250X, you have 2 GCDs, so you have 2 times as much, which is amazing. The big difference was to in order to address HPC workloads, MI200 introduced some very fast metric score for double precision. So now you can perform way more matrix operation, or kind of thanks to this matrix score, that's what we call it, which is something that you could not do for MI100. So MI200 really tried to target HPC on that front, like double precision becomes way faster for matrix operations. Another thing that really improved was something targeting machine learning, which was the BrainFloat 16 instruction rate. It doubled for BrainFloat 16 and it doubled for int 8. Any questions about this? Okay. And this is how it looks like. You may have seen this from other presentation, but this is one GCD. And you have 2 of this connected through this Infinity Fabric link that are extremely fast. In fact, you can do up to 400 gigabytes per second bidirectional traffic, peak, of course, when these 2 GCD are connected via this 4 Infinity Fabric links. This happens for MI250X and MI250. 250X is what you have on Lumi again. And if you have an MI210, you will have just one of them. As I said, TSMC 6 nanometer technology, up to 120 CUs, which is what you have on the top of the line MI250X. And I said, you have this new matrix scores per matrix scores that improve the HPC and machine learning workloads. If you have a HPC workload that also uses FP32, you get a 2x boost potentially if you use some FP32 operation that are called packed FP32, which double basically the throughput for FP32 if you do a few things in your code, which is fairly easy to do if you program in IP. Okay, it's just to show you what we're dealing with here. Very commercial-like slide. ROCm 5.0 has been around for a while. Now we have 5.3. We released 5.4, I think, yesterday or the day before. So this is kind of sort of outdated, but the gist is that now we support Navi cards. So if you have a Navi, even a retail card like RT 6800 XT, which is a Navi 21, that you buy at your favorite store, you can actually use ROCm on it, and it works out of the box. I know because I tested it on my personal one. It's pretty great. And then you have lots of optimization for MI200. You have the FP64 matrix operation supported in software, improved cached, and so on. Runtime got improved a lot, but also we launched this support. Actually, we improved the support for MLL frameworks and more HPC app that you can actually download in a Docker container from AMD Infinity Hub if you want to try our hardware and you don't want to deal with all the pain of installing a new software stack and applications and so on. Any questions about this? Okay. Machine learning, deep learning, and AI. So I don't know how many of you have deep experience with machine learning, and for this reason, I felt need to clarify a little bit the jargon. So I'm sure you have seen this Venn diagram a lot in your life if you're familiar with AI and machine learning, but it's good to explain the differences and the overlaps. So we have this big circle, which is AI, and it's a very general set that includes all the techniques that enable a computer to mimic human behavior. If you have a code that has an if-then else statement that says, say hello, and if you see an input that says hi, you say how are you, and it mimics the behavior of a human, that's AI. You don't need anything fancy. You just need to mimic the human behavior. The real deal is when you introduce ML, which is a big chunk of AI. Is there a question?
Let me just mute someone who.
Okay.
So
ML is a pretty big deal. It's the set of techniques that give the computer the ability to actually learn something without being explicitly programmed. And the way they learn is it's learning from the data. So you have a bunch of data, you have a model, and you try to teach this model to do certain things based on the data you are putting into input. Then you have, in a smaller subset within ML, neural networks, which are models and techniques that teach a computer to process data like the human brain. Why are these very good? Because they are able to model nonlinear distribution, which is very important when you have very difficult problems. What's the drawback of neural network? Well, the drawback on neural network is usually that you require a ton of data to teach these models, very sophisticated and nonlinear models, to do what you want them to do. Deep learning, it's a smaller set of these neural networks because when you say deep learning, we use the neural network with 3 or more layers to basically this gives the ability to the neural network to model even more complex distribution because you add more learning power, let's say, with the number of layers that to stack one after the other. And of course, there are various architecture. There are recurrent neural network, convolutional neural network, and so on. But that's the gist of it. And finally, one of my favorite of all times, reinforcement learning, where it's kind of transversal across the deep learning neural network and machine learning, depending on what model you use for kind of model the state, the action state function. That's something that if you want, if you're interested, we can talk about later. But you use machine learning and deep learning model to learn how to achieve a goal in unexplored, unpredictable, or uncertain environments. And it's basically the learning is based on rewards and penalties, and it's extremely powerful. Any questions about this? Okay. Very commercial-like slide. We now support the main ML framework entirely, I would say. TensorFlow, PyTorch, and Onyx. We support also the lower layer where this basically machine learning networks rely on, like JAX, DeepSpeed, or CuPy. And everything works with the ROCm and AMD Instinct accelerators. And the presentation of today is to basically show you how this is true. And if you have any questions because you tried and you failed, I'll be happy to answer. I will not teach you anything about the basics of machine learning or deep learning. We'll just go through TensorFlow and PyTorch, how to install it, how to find the documentation on how to install it. how to run it, what to run, and how to test it, things like that. Very practical. These are the ways that we can actually, we currently use to install these frameworks. So we have, you can build it from source if you want. If you're a little adventurous, it's not too difficult. It takes some time, but it will work. If you are not interested in learning the installation process, you can use you can just download the container from Infinity Hub and use it in a Docker container, and works out of the box. And if you are kind of in between, you can use pip, which is what we do today. So you have some freedom to install it where you want, and if it's not installed, you can install it pretty easily without downloading a Docker container in case you don't have sudo, which is usually the case when you're on a cluster. Same thing for PyTorch. It's pretty much the same process. We're going to install TensorFlow and PyTorch via pip. And same things for the other, even though there is a little less support, for example, for JAX, I believe. I'm not sure the status at this time. But there are links here, and George has already the slides in case you want the slides available. This is just a slide to tell you that we have supported and sort of optimized our gradient support for TensorFlow and PyTorch with the most used models on Hugging Face. So you have all the ResNet, VGG, Inception, GoogleNet for image recognition. You have the transformer for language processing, and you have all the DLRM for the recommendation engines. These are being tested and optimized with our software stack. This is what I was mentioning before. It's the AMD Infinity Hub. It's a website where you can download Docker containers of some of the most used HPC and apps, and including also the main framework for machine learning that we support. So you just go to amd.com Infinity Hub, you download it, and you run your workload and see how it performs on AMD hardware. This is a fairly useful slide to use offline to see all the various differences between MI100, MI210, MI250, the CDNA architecture, more details on the CDNA2 architecture in a white paper, which is technical but not overly technical. It's very useful if you're a developer. This is probably the most important page that we're going to use today. It targets 5.2. I am running on the ECP cluster, which has 5.3, so it's going to be slightly different, but I'm going to guide you step by step from docs.amd.com, where we then get here, and then we'll get all the information we want. Any questions about the previous slides? Comments? All right. TensorFlow, that's one slide. So what is TensorFlow and what is Keras? Because sometimes they are used interchangeably, which is, in my opinion, a mistake. So we should probably clarify what they mean and how they are connected. So TensorFlow, which we will call TF, is an open source library for solving problems for machine learning, deep learning, and AI in general. The focus is on training and inference of neural networks, but it does other things as well. It allows users to write their codes in either the functional style or a more object-oriented style. And you will see what I mean by this when I show you the codes of PyTorch, which it's more object-oriented in terms of Python approach. Supports multiple accelerators, meaning that you can use on our hardware or the competitor hardware, also on the Google hardware, the TPUs, but you can also use it on multiple instances of that hardware. So if you have a node with multiple GPUs, you can actually distribute the load very quickly. And I have at least one demo for this that it's pretty useful, I believe. Why is TensorFlow and Keras usually used interchangeably? Because initially Keras was designed to be a high-level API for building neural networks, and it supported mostly two frameworks underneath. One was TensorFlow, the other one was Theano. And in 2017, Keras was adopted by TensorFlow. So now you can use Keras by just calling it as part of TensorFlow. That's why it gets usually mistakenly as saying, oh, I'm using Keras, and they mean I'm using TensorFlow because now it's been absorbed. As I said, we have two options to install a ROCm-aware version of TensorFlow via Docker image, which we are not going to do today, and via wheel package, which require you to have Python 3.7 or above. We're not going to build it from source, so it's not even listed. This is very important if you want to build it. Depending on the cluster, you have to get the right version here. Instead of 5.2, you may want to use 5.3 or 5.1 or 5.4 as soon as it gets updated, because it has been released a couple of days ago. And we are going to use for the presentation this, mostly this directory, which has lots of tutorial examples in a Jupyter notebook, but you can also download more examples here. So in case you want to follow what I'm doing, I'm going to use this most of the time. Any questions on TensorFlow? Okay. PyTorch real quick, and then we're going to do the demo. So PyTorch is also newer than TensorFlow. It's been developed by Meta, ex-Facebook. And PyTorch is an optimized tensor library for deep learning using GPUs and CPUs. It's very much object-oriented, and everybody out there calls it Python-like, and it's able to work on multiple accelerators. Again, it works on our hardware, competitors' hardware, and also can scale out on multiple GPUs in a node or even across nodes. Popularity is increasing in the AI and research communities, and again, we have two options to install ROCm-aware version. If you don't want to build it from source, Docker image, wheel. Another thing that is very important, this is probably a mistake in the slide. It should have been another bullet point outside of the numerator enumerated, is that if you plan to start to build a new model now, and you want to use it on AMD hardware, keep in mind that AMD is now one of the founding members of the PyTorch Foundation. So you can expect that AMD will support PyTorch for a long time, and it will be very responsive. So if you have your TensorFlow model and you have been running for 4 years, that's fine. TensorFlow support for AMD is not going anywhere. If you are starting now, if you plan to migrate to PyTorch, that's a great idea, because AMD will be tightly working, basically help to elbow with the PyTorch Foundation. Again, some links. Personally, I am more a TensorFlow guy, so you will see way more material on TensorFlow than on PyTorch, but it's just because I am more fluent with TensorFlow instead of PyTorch. But most of the examples will be for PyTorch will be taken from this repository for tutorials. There are other and also examples. Tutorials are connected with certain presentations online, so it's better as a study material, but for an interactive demo, examples are probably going to be better. And if you want to install it, I will show it to you later, but just go on pytorch.org. There is this little form on the web page that's interactive. You click your system, you click how you want to install it, and you'll get a magic word to magic command to just install everything in pip, and that works just fine. It's a little misleading, so that's why I will tell you how to install it because of the versions. But if you follow the documentation that we have online, you'll be fine. And that's it. That's the presentation. Do you have any questions about all this material? Okay. Let's dive into the presentation, into the demo, actually. Okay, so I'm going to make this a little bigger if I can. So this is I'm on Windows, as you can see, and I am on the ECP cluster that we have at AMD. I think you have some training. I have a training profile from ENCCS. So I'm trying to mimic a regular user for your training. And I just got on a node with an MI250. I managed to run a Jupyter notebook after installing TensorFlow, and I'll show you in a moment how to install TensorFlow by using a tunnel, which is an SSH port forwarding. If you're on Linux, you just have to do like SSH-L and set a few ports to the right node. But if you have, mobile, you can just do the tunneling and set everything there fairly easily. If you don't know how to do it and you're interested, I can show it to you later once we cover all the material, but it's easier than it sounds. This allowed me to basically connect to the local host, but actually I'm connected across the ocean to the cluster that is based in Germany. And I can actually do interactive work from here. It's very fast, but actually it's running on the cluster, on the compute node. So I have 8 GPUs, 8 GCDs available for MI250 running for me. Okay, let's see how to install TensorFlow first. I have this node open so I can show you the usage of the GPUs, but also to show you how to install things in the environment as a virtual environment, if you care. So first of all, we need to check the Python version we are using, because I told you that TensorFlow needs at least 3.7 or above. We are running 3.8, so we're good to go in this case. How do we install it? Well, we go on docs.amd.com and we go to ROCm version 5.x. Why 5.x? Because if we check which version of ROCm we are using, we see that we have 5.3. And here. So we want 5.3. That's what we have installed. Click here. And then you have all this overwhelming stuff. You can ignore that for 5.3.3, 5.3.2, 3.3.2. You go to the regular default 5.3. And you go down to Deep Learning Guide. I'm going to make this a little bigger, even though it's not super important. And here you have all your guide on how to deal with deep learning. You go to Framework Installation. And here on the right, which you have to navigate a little bit this, that's why I'm showing to you. It can be a little misleading. You go to Installing TensorFlow. And you have option 1, which is what I told you before. We're not going to do this. We're going to do option 2. And what you do, they tell you to check if you have a Python version that it's compatible with this. If you don't, you have to install it. And you have to configure all of this. I have already done all of this, upgrading pip and so on. The most important part is this. And basically means that you need to use a specific wheel version to make sure that it's compatible with the ROCm version you have. Which version is this? It's the one listed here. You open another page, you go here, you find ROCm 5.3.0, click, and that's what you're going to use for your pip command. All right. So what I usually do is I create a virtual environment first. So I have my stuff separate and I don't get a package with everything for PyTorch, TensorFlow, and everything. So what I do is, for example, I create a new environment. I already have one, so I'm just going to create this TensorFlow new env in my home directory. And this will create a directory with some scripts inside. You just need to source in it. And you're good to go. You'll see this little thing here that tells you that you are in an environment with TensorFlow. First thing I do, upgrade pip, which was already mentioned in the slides, in the documentation here. I tell you to upgrade pip. And after that, all you need to do, sorry about that. I lost link. That's all. And this will download, of course, I have everything cached, but this will download the right version of TensorFlow for ROCm. And you are good to go. All you need to do is this, and you can just run TensorFlow right away. If you want to test it, you have to do this. You can do it in other ways, but that's the recommended way of doing it. Okay, let's see. Success. We have a GPU-enabled TensorFlow for us. And That's how we install TensorFlow with pip, and everything should work. I installed a Jupyter notebook on a different environment. I'm not going to use this for practical reasons, and it's here already running. So I've been running some tests before joining the call. And basically what you do is this allows you to run Jupyter Notebook without a browser on a specific port on all the addresses, basically. You open this with this particular token in your browser. It pops out a window that it's interactive. And as soon as you start doing this, you'll see that the number of devices that you have available and visible to TensorFlow. And as we were hoping, since it's a MI250 node with 4 MI250, we see 8 GPUs because we have 2 GCDs per MI250, which is a great amount of GPUs, you'll see. After that, you see all these messages related to Rock Fusion that is enabled, which is a good news, but it's very verbose. And I haven't had the time to actually find a way to stop the verbosity, but if you see this message, it's a good sign. Everything is working as you may expect. This is something that I was doing running 2 Jupyter Notebook at the same time, and you will see why you get this in a moment. But if you run just 1 Jupyter Notebook each time, you will not have any error messages, hopefully. So let's dive right in. I open this, and I have this ML training, which is a directory that I have. And when you download the TensorFlow docs, which is the first link that I showed you in the presentation from GitHub, it's all public material. You can do Cite, English, tutorials, and these are all your tutorials that you can play with. We're going to start with a quick start, and we are going to have the beginner version. Just going to open. And this is just short introduction on how to use Keras. So Keras is called the easy way of using TensorFlow, the beginner version, because there is another way of using TensorFlow that does not involve Keras, which deals with explicitly mentioning all the steps of a training of a neural network. So you have the forward pass, the backward pass, the application of the gradients, and in a loop, in a training loop. So it's called the custom loop or advanced TensorFlow version of the custom approach for TensorFlow. It gives you a little bit more control and allows you to do more researchy things. But if you want to just play with a neural network that is already exposed by Keras, this is the easiest way to do it. How do you do this? Import TensorFlow. You get some messages here, nothing to worry about. You download, in this case, a data set. It's the handwritten digits. It's the minced data set. You need to normalize the pictures because they're in grayscale. You have to make it black and white. And after that, that's how you do a neural network. You create there are many ways in terms of syntax. This is the easiest, probably. You have a model, which is a sequential model. And inside the sequential model, you have 4 layers stacked one after 3 layers, let's say, stacked one after the other. One is the input, which takes a 2D tensor, 28 by 28, which is your picture of the digit. And then you have a dense layer with 128 neurons and an activation that it's a ReLU activation function, which is a nonlinear
Excuse
function.
me for interrupting a lesson. Could you just zoom in a little bit to your notebook there so we see it better?
Sorry, I didn't get your observation.
Could you zoom in a little bit?
Yes, absolutely.
It's larger, maybe 2 more.
How's this?
Yeah, could you do 1 more?
Yes, I can. Yes.
Thank you.
Yeah, it's way better, absolutely. Thanks for letting me know. So we have the data set, normalization, and then we have the model. You have an input layer, dense with layer with strongly connected, also called 128 neurons, and an activation function right after the layer to make it nonlinear. Dropout, which is a regularization technique that allows you to deactivate some of the neurons, which allows you to avoid overfitting at the end. And at the very end, you have 10 neurons. Why 10? because this data set is for handwritten digits. And how many handwritten digits are we have? We have 10 possible outcomes from 0 to 9. And each neuron here will tell us, once trained, which one is the one that the model believes it's being passed as an input. So you pass an image that has a 4, and the model, when it's trained, will light up the 5th input more than others. And then we will use an activation function at the end to make sure that this light up will be mathematically optimized in order to have some training. What you care about in terms of ROCm is that when you have the model here and you have this little hourglass, it will build this model and it will give you all these messages. There is nothing to worry about. Everything is great and it's normal. You have all 8 devices, and this is something interesting that I wanted to show you, so you understand what I mean by running out of memory if you run 2 Jupyter Notebook at the same time. TensorFlow, in particular with Keras, it's very greedy, and it will take all your memory on the GPU, all of it, even if it doesn't use, if it uses a 1% of it. So if you try to run 2 Jupyter Notebook at the same time, you will have an out of memory error, because TensorFlow is extremely greedy. You do this, for example, I'm on the compute node and I'm running ROCm SMI. See that I'm running just on a GPU, of course, but 98% it's taken. It's doing nothing, but it's there. So nothing to worry about. It's totally normal. We try to make a prediction on the model here that it's not being trained. And the output, it's some nonsense. It's the first output of the 10, it's 0.6. The other one is 30, almost 30.34. One is negative. The other one, it's 61. Makes no sense. What we want to do is to pass this output to a softmax layer, which basically will make sure that the 10 outputs will add up to 1. So it transforms this nonsense to a probability, which somehow adds up to 1. And the higher probability will basically represent what the model believes is the answer, the right answer. So in this case, we pass, I don't know what number is this. We can print it out if you want, but the model has no idea because they are all very close, more or less. You can see here, I'm just running it. And as you see here in the output, it has some preferences, but not really. Everything shines because the model is not trained. To make sure that we have an answer like it's number 3, instead of looking at the numbers and say, oh, number 3 it's higher than number 5 or vice versa, we have this this logit. Basically, it's a sparse categorical cross entropy function. It's a loss function. That's why it's called. You define the loss function, you make a prediction, and then you pass to the loss function here, and you see that it's close to 0.2, which means that the model has no idea what the right answer is because it's close to random. And you can see this concept expressed here. Close to 2.3, it's actually a little less than 2. It doesn't really matter. The model is not trained. We compile the model with an Adam optimizer with default parameters. We have a loss function that we defined before, which is the sparse categorical cross entropy. And then we want to use the metric of accuracy in terms of to see how good the model is doing. And finally, we train. We train on X, that's the input, Y is the output, and we run for 5 epochs. And this is where the fun starts. It's running on the GPU. How do I know that? I go here, see 2%, 12%, 16%. It's very fast. The model, the GPU is so fast that you will not see it going very high. It's done basically, but you cannot see it going very high with this little model. But yeah, basically what you see here is that the accuracy from 41.41, it goes right up to 91, 95, 95, 96, 97. So it's actually improving, which is what you want to see from your model. You evaluate your model, and you see that on the test, basically you get an accuracy of almost 98%, which is fantastic. So now, if you want a model that returns the probability, you just need to do another model, which has your model and a softmax layer, which is the final activation function that I was mentioning before, that will tell you number 5 is the best. This returns the probability, and then you have the activation function that will tell you number whatever is the best. But that's how it works. So you have you can see now that the probabilities are on the test. So it's something that the model has never seen before. So on a new data set, basically will tell you, yeah, 99%, I'm sure it's number 0, 1, 2, 3, 4, 5, 6, 7. This was number 7. And all the others are very low. So model is very confident that that's a number 7, that it's passed as an image. And that's it. This is the beginner presentation. It's extremely easy to do a neural network and some training with TensorFlow, and it goes extremely fast on GPU, as you can see here. It takes 4 seconds for each epoch. Are there any questions about this simple example? Okay. Let's close the beginner, because otherwise I run out of memory, and let's open the advanced. That's the very same problem. I'm not going to go through all the details because it's exactly the same. I'm just going to go through the differences between the two. We import this. We normalize the model, the input set, the data set, and then we start slicing it in batches of 32. And now this shows you the first difference. This is fine. The first difference in terms of building a model, just to shake things up. Previously, you did not have to create a class. Now, still, you do not have to create a class, but it creates a class to show you that TensorFlow is actually also supports object-oriented programming. So you can actually create a model as a class that has a constructor, if you're familiar with C++, and as soon as you call the model, the constructor will build the neural network as you define it here. So you have this convolutional 2D network, which takes 32 by 32 conv2D network with 3 channels, I believe. And then it passes it to, it flattens the input, passes it to this 128 wide dense network, that's dense layer. And then it passes it to the output that is still 10 neurons. When you do this call, it will basically build the neural network. It will just create this. Sorry, it will pass the input to the neural network. So you have X that goes into conv1, which is whatever it's defined inside the model. The output will be still X, that will pass to the flatten. Again, X pass to the D1, and then returns the D2. So this is how you call the neural networks in terms of passing it through the network and forward. And right away, we create the model. And this already calls the constructor and creates the neural network just by calling this, very object-oriented. We then, well, we execute it. Then we create the loss function that I told you before. We create the explicit optimizer, Adam, which before we just called by name. And we create the metrics for the train loss and test loss and accuracy for both. And this is where the fun starts. We have to create now explicitly a training loop. And that's how you do it. You have to define this TF function. And then you have to create this context in the TF gradient tape. What you do is, pass the images to the model, and this is basically invoking the call method of the model. You say that you want the training to be true, so you actually have forward and backward, that it gets forward mostly in this case. You have your prediction, so you pass from the input to the back, and then you want to see how wrong you were with this prediction. So you use your loss function to see how the prediction matched with the label. You will have a loss function, and at this point, you can do the backward. you can apply the gradient, the loss function, to the training variables to modify basically to apply the gradients and correct the network for the next pass. And that's how you apply the gradients. You print again the loss, the train accuracy, and you're good to go. It's basically what Keras does under the hood. You spell it out. That's what it is. The test step, it's pretty similar. It's a matter of just passing it without the training, because in test you don't want to train on the test. You just want to see how good you're doing. So you don't have the gradients and applied gradients in here. And then you have the loop over the epochs, and that's what you do. You train step, test step, and then you keep going and you print out. And again, this runs on the GPU. And you see how this is already changing pretty well. But yeah, that's how you do it with a custom layer. It's a little more explicit, but it can be useful when you have to build more complicated networks. Are there any questions about this? Okay, let's do something.
I have a new question. You were referring to model, and in machine learning, if I go to Infinity Hoop or somewhere and download a ready model, or so, does that mean that someone has constructed a smart neural network, but it is still untrained, or is the model already trained network? What's that mean?
Okay, so that's a very good question, and I have an example on that. You have basically you have models that in this case it's incredibly small, and you can always train it from scratch because it's so fast. Okay, there are other models like ResNet 50, which is incredibly big. It's I think 50 layers. That's why I think it's called ResNet 50, and it's trained on a huge data set, and it takes weeks to train that thing based on your architecture. And that is used for image recognition. Okay. If you want to do image recognition on your desktop and you do not have the power to train that big model, TensorFlow and other frameworks will give you the model that has already been trained on a very large data set, so that model, you can just use it out of the box almost, in case you need just to recognize to the same thing that the model was trained to do, because the weights have been already trained. But you have to download that specific model. And I have an example, so that will clarify a little bit better. This case, you are not downloading a pre-trained model. You are downloading a new model that you are building up. If I want, I can modify this model to make it more powerful by adding another layer here and another dense layer with, I don't know, 64 neurons. And I can see how that changes my performance in terms of accuracy. But I have to train it myself because that was not pre-trained. It was just the weights were all random. Does that answer your question for now?
I guess so, but I mean, if I go, are all the models that you download already pre-trained?
Most of them, yes, if you download them in a way that I will show you in a few minutes. I have an example, and I'll show you what I mean by downloading the model. Here, you are not downloading the model. Downloading the model is something that you go on TensorFlow and you say, I want ResNet 50, and that will be trained for you. Will be already trained, and you can use it almost out of the box. What you will need to do is something called transfer learning, which basically means remove the top layer of the pre-trained model and add your layer so that it can be just that layer, the new layer can be trained to do what you need to do. And I have an example again. So if you indulge me for a couple of minutes, I will show you what I mean by that.
Looking forward to it.
Okay. Let's close this puppy. And I want to show you something fun. Generative model and DCGAN. This is something very advanced. You don't need to understand all details, but it's just something that shows you the potential, and we'll start seeing some performance out of it. What is a GAN? In particular, deep convolutional GAN. It's a generative adversarial network. So right now I showed you a model that does classification. You have a digit that goes through a neural network, and the neural network tells you if it's what number that is. It's very useful, but it's a classification problem. You can do regression. For example, if you want to estimate the price, the housing prices of Boston, let's say, based on a certain data set, the number of, time of the year and whatnot. And that is a regression. It will tell you a number. It will not tell you which house to buy. It will tell you a number that is the price of a certain house, let's say, in a certain area. The third thing that you can do with general machine learning and neural network is to understand the distribution of data in a data set. And by understanding and learning that distribution, you can actually generate new data that is completely synthetic thanks to this neural network. And these are called generative models. They are the most complicated model you can do in terms of complexity and capability of the model. Very, very popular if you are into what's going on the internet with also stable diffusion is GANs. Sorry about that. The GANs are basically two networks that are one is a generator, it's the artist that learns how to create images that look real. And then you have another network, which is called the discriminator, which is the art critic that learns to tell real images apart from the fake. And this is fascinating. If you train these two networks in a coupled way, and they learn pretty much at the same pace, one improves the other. And they are so good at a certain point when they converge that the discriminator, it's very, very well trained to tell fake and real images apart, but actually still manages to get fooled by the generator. And at that point, the generator is so good at generating fake images that look real that you can get the generator and generate a whole synthetic data set that looks real, but it is not. And this was a big splash in the machine learning community when they started generating fake faces from celebrities that looked real, but that celebrity never existed. So let's see how we can do this. So we just download these things. It's downloading some dependencies here. Just including some stuff. And again, I'm going to use the data set that is the MINST. So we are going to generate fake handwritten digits because we learn how the data is distributed. We know that the data set is 60,000 images big. We decided that the batch size is 256. If you don't know what the batch size is, I can tell you all about it later. At this time, 256 is a good number. And let's create the generator. So we have lots of good messages here. This is the network. This is the functional way of using TensorFlow, like the beginning example. So we're using keras here, and we're using just very simple functional style to program this. We have a network that is dense with this particular sizes. The input is 100. And I'll tell you in a moment why it's 100. We do some batch normalization that is used for stability. We use different activation function, which is called the leaky ReLU, nonlinear, more flexible than the regular ReLU. And we start basically this conv2 transpose, basically something that takes a flattened set of inputs and it starts creating a 2D images thanks to this. So this 2D is where the rubber is the road when you start generating an image with this 128 layers, basically 128 neurons, sorry. You keep expanding, so you add another convolutional network that still is 2D, it's a little smaller, and then at the end you have just another convolutional network, which is just one neuron, which generates basically the 28 by 28 image. So this is the generator. You start from a flat input of 100 elements, and I'll tell you in a moment why 100. And then you, at the end, you have a 2D image, 28 by 28. as I said before, this model, it's not trained. So once I try to generate something from this model, I get garbage. It makes no sense, and it's expected. Why 100? So how do I generate different images that basically will look something similar, but they're all different with random noise? The input, this 100 that you see here, is just an array with normal Gaussian distributed random noise. You give it as an input to the generator. The generator now is not trained, but the generator out of noise will generate something that makes sense. It's almost like magic. We need to train it though. Any questions about this? I know if you're not familiar with this, can be like black magic, but it's relatively easy to follow if you familiarize with these concepts. Okay, let's go to the discriminator. Discriminator is the critic, and the critic takes as an input a 2D image, 28 by 28 by 1. 1 is the channel, which is just black and white, and starts doing their nonlinear considerations, some regularization here. There is another larger 2D layer, and then it flattens everything. So you have all this 2D layer, the 2D layer here that becomes flat, and that flat all converges into one single neuron. Why one? Because the output of a discriminator is it is fake or it is real. So that's why we have just one neuron, because you just need to have binary option for an output. And that's it. You just make the model, create the discriminator, and you print the decision basically here. Decision is just how it's built. It says it's fake. 0, I believe it's fake. It's something that was mentioned before. But we define the loss function. The way you pick this is related to the problem. So I will not go into the details of why we picked binary cross entropy. But this is how you build you will have 2 different loss because you have 2 different networks that are training one after the other. You have the discriminator loss. Discriminator is the one that tells you if an image is real or fake. And this is what you get. You have the real output that gets passed to the discriminator, and the fake output, potentially fake output, that gets generated by the generator. You will see what the real loss is. You will see what the fake loss is, and basically thanks to this loss function here. And then you will put them together to create this new loss function that will be used to train the discriminator. No need to understand all the details. I'm just going to through what the code is. Same thing for the generator loss. It's going to be a little easier. Basically, the generator will use the cross entropy. Again, 0 is fake, 1 it's correct, 1 it's real. And at this point, you generate 2 optimizer, 1 for the generator and 1 discriminator. Then in this case are both Adam with the learning rate of 0.0001. This is an hyperparameter tuning thing, so this works fine apparently. Checkpoints are not super important in this case. And now we can define the training loop and what this looks like. Since this is very sophisticated in terms of coupling to neural networks, we cannot use Keras for the training loop. We have to do the custom loop, like a little more complicated loop. We decided to use 50 epochs, 16 example to generate, and we start generating the noise that will be used by the generator to create the fake images, basically. And at this point, I will not go in too much details because it's a little out of scope here, but you have this training loop. For each training step, you have the generation of the noise for the batch size. And then you generate a fake image out of noise. The discriminator takes the real images and tells you the real output. then the discriminator try to understand if the generated image is real or fake, and it's fake output. You create the generator loss. Basically, you get the value for the generator loss from the fake output, which is whatever the discriminator wanted to decided that the image was like, and then you do the discriminator loss. That's why you train two networks at the same time. Get the gradients. This is pretty straightforward. You apply the gradients, and then you have the training loop at the end, which does just what this calls this function basically under the hood. I mean, under the hood is pretty explicit, but then you have other things here to save images on disk and other things good for visualization. And at this point, we do the training. Training deep convolutional generative adversarial network is very taxing. So you will see that why the GPU is useful at this point. You will see the GPU is being used way more than the case before, previous case. Okay, to do it a little faster, I go with, oh, sorry. Watch. I'm gonna watch this. It takes a moment to load the data. You have your hourglass here, and you'll start seeing in a few seconds, hopefully, the epoch and the time that takes for each epoch to work. So as you can see, each epoch takes 2 seconds, less than 3 seconds. And you can see that the GPU is just cranking in 100% all the time, or most of the time. This is very useful because the GPU is really giving you a hand. I can tell you, if you run this on the CPU, it will take a minute per epoch. So you are going down from a minute to 2.77, 66 seconds. Bunch of messages randomly that basically will disappear. But these little images here, and that we go for 50 epochs, will tell you how good the generator is doing, basically, at a certain epoch. So you can see visually that the images are improving, the quality at least. You cannot make up the digits, but it's better than random noise. So you have, 3, a 9, a 7, 0. You can make it up, and they improve over time. But yeah, that's basically the difference. If you try to do the same on the CPU, it's gonna take forever. It's just one of the advantages of using GPUs, in particular for adversarial neural networks.
So there's a question from the chat. Why is it only using a single GPU and not the 8 GPUs available?
Very, very good question. I have an example on the distributed part of this, but it's not related to this. So here's the deal. This is a public presentation, and I cannot give you codes that I wrote, but I can show you code that are already there. So this particular code does not have the pieces that allow you to run on multiple GPUs, but it is possible. And I have an example right after this that shows you the distributed training for Keras. So you can actually put the pieces together if you want, and you can see how that works. It's using just one GPU because that's what it is. Okay, it ended, and the digits look way better than before. The training happened, and it's successful. Basically, you can see that these are all completely synthetic digits. What was the question? Sorry.
I don't know if it's easy to answer, but I'm confused. How does these two networks mix the actual training data and the generate data? How do this
Here
to get together?
Here. That's basically what I highlighted. The generator generates data from noise, and the discriminator takes the images that are the real ones, and also tries to predict the fake input. So here you may have it's fake or not fake, and here you may have it's fake or not fake. Okay, but we know which one are those. So the discriminator at this point does not, but we do.
Right. Now I get it. I mean, it needs to pick. It's like a Turing test, basically. And it needs
Exactly.
to pick up which one is the real one and which one is the okay. Now
How do you know which one is? You have to use the discriminator loss, and you pass the real one as a first argument, the second one as a second argument, and here you put them together. Basically, this is the we say that an array, the ones like this is a TensorFlow thing. It's the real. This is the fake. And if these two match, it's great because at this point the discriminator managed to tell the real from the fake apart. If these two don't match, like the fake is 0 and the fake is 1, which means it's real, and the 0 is this one is 0, the loss function will be worse for the discriminator. So it has to learn how to distinguish those two, basically. This is how it does it. This is how the Turing test does it. It's a loss function. And how does it correct itself? With the backward propagation here. Discriminator loss, discriminator gradient, discriminator optimizer apply gradients. It's fascinating. This is the gist of it. And that's it. This is just to create images on the disk. But if there are no other questions, I can show you the distributed part of it. Let's save this so it doesn't yell at me. All right. Yes, I have it here. Okay, this is just I modified this code by one line. Sorry about that. So this is the distributed case. Let me just go back to show you which one it is. It's the Keras one. It will show you how easy it is to run on multiple GCDs with Keras. Everything here is based on this distribute strategy, and I keep doing this error here, clicking. Basically, it's an abstraction for distributing your training across multiple GPUs automatically. You can do it manually, but if you use Keras and you don't want to deal with low-level data distribution, this will do it for you. How does this work? Copies all the model variables to each process. That's just a repetition. It's a mirror strategy. That's the default. And then it uses an all reduce to combine the gradients from all processes and apply the combined values to all the copy of the model. So you have, let's say you have 2 GCDs, okay? Just keep it simple. The model would be replicated on both. The data passed to each model would be different. And you do the training. So at that point, you are training 2 different models, but you don't want that. You want those 2 models to be coherent at a certain point and to exchange the gradients that have been learned by each model. So it's an all reduce. What you do, you have to basically synchronize and exchange this all reduce so that the gradient computed by all the other processes are exchanged, applied, and you are actually training one single model, but on different data, so it goes faster. It's basically different data, same code, SIMD basically, almost, but single code run on the same on different GPUs, different data on each, and then a synchronization at the end of each training epoch. Okay, so do this, and as somebody was saying, you can do at the moment I want to use 8 GCDs, okay, just want to go all in. But if you want to just focus on, let's say, the first 2 GCDs, you have to do this. OS, environ, ROC or visible devices equal 0 and 1 in this case. You could have put 0 only, or if you want to test it on the CPU first, you can do equal -1. And that will completely deactivate all the GPUs. Again, our favorite data set of handwritten digits. And all you need to do is creating a strategy. I want to show you something. You have to create a strategy, basically. And the mirror strategy is what you want. It will find all the GPUs, and then you say, how many GPUs do I have in strategy number replicas in sync? 8. And now you have all the GPUs allocated. doing nothing. If you open another disk of another of these guys, it will say, "Oh, I don't have room. I don't have RAM." Okay, this is very important. How do you take advantage of these GPUs in the machine learning environment? So when you train a model here, I'm just reading, on multiple GPUs, you can actually use the extra computing power effectively by increasing this thing called the batch size. The batch size is basically the amount of data, of the part of the data set that you want to train in one single shot, let's say. Why is bigger better? Because the GPU has more stuff to do in terms of matrix multiplication and various, gem operations, convolutions, if you want, depending on what you're doing. And they are using lots of more compute power. If the data set, if this batch size is too small, the GPU will be fast, but on a distributed environment, you will be paying lots of cost for communication because the GPU is doing so little that it's not really worth it. So before it was 256, okay? Right now, I decided to put it to 10,000. I can put it to whatever I want here. The data set is 60,000 big. I'm going to do just 1024 just to see how it goes. Actually, let me do 256 and show you how little the GPU does. And then we're going to improve it a little bit to see how it improves. This basically says that the batch size will be the batch size per replica. So the number of GPUs we have, the batch size 256 multiplied how many GPUs we have. So 8 multiplied by 256. So this, scale the data set as we have done before. We divide it between training and evaluation. We create the model that we created basically before. This is just for classification, but we are doing it in a distributed fashion. Model got created, everything is good. You don't care about this stuff much. It's just for model checkpoint, when do you need to stop for the learning rate, TensorFlow stuff. I'm not going for explaining you what it does. We're going to train for 12 epochs, and we're going to use these callbacks to help stop when it's not needed to train more. And we are doing it. You're seeing a bunch of messages here. Go here, and we should see something moving soon, I believe. Yep, there you go. And it's doing it. So we're doing training on multiple GPUs. Yeah, it's going.
So there is a question in the chat. Could you start a second notebook and select a different GPU to work in parallel?
I can do 4 and 4. Yeah. I can do 4 on the first notebook and 4 on the second. Yes. That should be possible. You can try it. Okay. That was done. I just want to show you, well, if you put a bigger batch size, you will see the GPUs going a little more to 100. That's the deal. Let's do this. I think I can open another one of this. Yes. All right. Let's see the status here. All zeros. That's very nice. We should choose just the last 4. See? And then we have this. The first 4. Okay, this is already running. This is probably there are parts of TensorFlow that I think they call the same stuff. It's not the GPU stuff. It's something inside TensorFlow. As soon as this is done, I believe the other one should go. It's waiting on something. So ideally, yes, you can do it, but you need to do something else. You need to make sure that you run it at the same time, I believe. Right. So in theory, yes, it is possible, but I think we need to try something a little less random here. Okay, let's try again. I never done it, so it's also good for me to see the limits of this. But let's do it again, just real quick. And I'm gonna stop right before calling the training, okay? Okay, stop here. Stop here. No, it doesn't let me do it. At least not on the Jupyter notebook. I believe you can do it with two different processes. So you have the scripts. You can do it, I'm pretty sure. But with the Jupyter notebook, it doesn't let me do it. There is something dealing with the same server, I think, that bugs it. Mostly because there is the same process. One is setting 4 GPUs, the other one is setting the other 4 GPUs. But I'm pretty sure you can do it with a regular script on 2 different calls. Because then why not? All right. Sorry about this. We can try that in a moment if you want with a script. Okay. Any other questions about this? It's extremely simple. You just need to define the strategy. And if you want to squeeze some more performance, this is just the gist of it. Define the strategy, the mirror strategy, and then you use it with this. If you want to squeeze some more performance out of it, and that's it. Yep.
How does one know if the underlying interconnects are supported by the specific version of TensorFlow you download for in a specific case, say in Lumi? How do I know if the Slingshot is properly used or not?
So in this case, we are not using Slingshot because it's one node. If you want to use multiple node, it's slightly more difficult because you need to deal with actual network ports, or you have to rely on Orobod for going on multiple nodes. This is just one GCD, but everything it's delegated to this layer called ROCm, RCCL, ROCm, which is the ROCm version for Nickel, which is the NVIDIA version. And it's just something that it's highly optimized for machine learning in general and masks this complexity to you. So TensorFlow calls ROCm, and whatever ROCm decides to do, which you can have some control on it with some environment variables, that's what happens. So it's all masked by ROCm.
Thanks.
Yeah. Any other questions about this?
There is one question from the chat. How would the 2 Jupyters exchange information?
They will not. The Jupyter notebooks, you mean?
Yeah.
They will not. There is no need to exchange information. Those are 2 different instances, let's say. And I don't see why these 2 should communicate, to be honest. 2 different instances. And also Jupyter Notebook is mostly for demos and things like that. Those are 2 different scripts. You can see it as 2 different Python scripts that run independently. If you want them to communicate, you have to do something else. But I don't really see a use case for having 2 Python scripts to communicate with each other for training networks, training neural networks or TensorFlow. So they don't. That's the answer. They do not communicate. They're independent. you see some interference here because the process that actually is launching stuff, it's just this guy here, this Jupyter Notebook single process, which is spawning two different, let's say, instances of a notebook. But in the end, it's one single process. So that's why it doesn't work when you set two different ROCr visible devices, because it's the same process. I believe if you run two different Jupyter notebooks, like one instance here, you open another shell, you run another one, and then you have two different browsers completely, two different instances, that should work, which is the equivalent to having two Python scripts, two different Python scripts, if that makes sense. This is one spawning different tabs on the browser, pointing to the same engine, let's call it. So there is an interference. When you have two of this Jupyter Notebook processes spawn across two different shells, let's say, you should be fine. Let's close this. I think I'm done with the TensorFlow stuff. How much time do we have?
There was just sorry, there was a follow-up. Okay, so are they just doing the exact same thing twice? Maybe you already addressed this.
Okay, so they are just doing the exact thing twice? Yes, they are. Yes. Yes, basically that's what it is. So in the distributed case, you have one Jupyter notebook and you're using 8 GPUs, okay? And you have the distributed mirror strategy. You'll have the same model in terms of structure of the neural network, doing the same operations on different data. When I spawned two new Jupyter notebooks, one on the first 4 and the other on the other 4, I was doing it within the same process, so the same Jupyter Notebook engine, but they were doing the same thing. There was no communication across Jupyter notebooks. There were just two separated instances, and I was just trying to see if I could use 4 GPUs for one case and 4 GPUs for another case. Let's see, you want to use one data set on one case and one data set on the other case, but you can do that if you use two different engines like this. I can close it and show you what I mean, if that helps. So I close this. That helps to clarify. Okay, so this is how I call one Jupyter engine. Okay, I do this, and that starts and it spawns one engine basically. Then I open another instance on port, let's say 8889, and then another server pops out, so I can open it, for example, in another tab on a different port. And at that point, I can run two different instances of the notebooks on different GPUs at the same time, but they do not communicate. There is no need for them to communicate. The communication is within the same notebook for the distributed case. So it's another layer of parallelism, if you want. In case, for example, let's say your machine learning case does not scale on 8 GPUs, it scales only on 4, but you want to test two different data sets on the same model that you have that scales on 4. You grab one node of Lumi, you split it into 2, 4 GPUs for one data set, and then independently 4 GPUs for the other data set. Did I confuse you more? Or it's clarifying? Okay. Let's keep going just for the sake of PyTorch, and then we can answer some question if you want. So how do I get out from the TensorFlow environment? Deactivate. So the TFM that was here, that was there before, it's no longer there. How do I enter the PyTorch? I do this again, like before, and now I can use PyTorch. I'm good to go. Let's check the system. It's nice. Nothing stayed there in terms of resource utilization. I go inside. So unfortunately, PyTorch does not expose the Jupyter notebook. They are just scripts. So you'll have to be with me and use the editor to see the code. PyTorch examples. Okay. If I'm starting from the examples just because it's easier to run. running this example is a little tricky because you need to download a bunch of data sets. And for some reason, one data set is 48 gigabytes and I didn't download it, and I don't want you to download it for a tutorial. But let's go to the DC-GAN example again. That it's the deep convolutional generative adversarial network example, the one that generates images. And when you open this directory for PyTorch, you'll not have all this stuff. You will not have this data directory. I had to create it to get things running. What you do is you read README always, and it will tell you what to do and how to use this script in particular. So right now, I'm going to show you the code and just the difference between PyTorch and TensorFlow. You can see that it looks quite different because everything is a bit more object-oriented, Pythonic, let's say. Sorry, before I go to PyTorch, there was this question about transfer learning. Sorry about that, I forgot. Let me go back for a moment. So the questions about downloading the model with pre-trained weights. Apologize, I forgot about that. Let me re-enter the TensorFlow environment. I'm good to go. This is something that I cannot give you, unfortunately, but it's very easy to understand. This is a code that I wrote. Okay, so what do I mean when I say you can download the model that is already pre-computed, pre-trained? Keras allows you to do things like this. So you know that this ResNet 50, it's a model that it's very widely used in the community, and it's huge, and you don't want to train it yourself because it's huge and it takes a long time, and you have to download this big data set, which is ImageNet here in this case. And what you can do if you want to use it just for feature extraction, it's the so-called transfer learning. Transfer learning means that you have a model. In general, this is just generally speaking, you have a model that is trained on a data set, big data set, and then you can basically take this big model, this big neural network, remove or add to the last layer, one layer that it's trained just for the stuff that you care about. Let's say I want to have a model that extracts the faces of the people in this Zoom call, okay? The model doesn't know it because I don't even know you, honestly. I've never seen you before. But if we have some pictures with the names under it, we can use ResNet to extract the main feature of the picture and then train just the last network to say if a picture is Alessandro, another picture is Bob, another picture is George, or any of you. How do we do that? We download the model, the ResNet, already trained with the weights of coming from ImageNet. What does it mean? ImageNet is a huge data set. And this model, this ResNet, is the neural network. The neural network that I'm getting here is the ResNet 50, already trained, ready to go on this huge data set. And that's it. All the weights are trained, you're good to go. What I'm doing here now is I want to use this data set, this Cypher 10, which is a very well-known data set that has stuff inside, pictures of stuff. But that stuff belongs to one of these 10 categories. It's either an airplane, an automobile, a bird, a cat, a deer, a dog, a frog, a horse, a ship, or a truck. This network has not been trained for this task. So what we can do is we can use the ResNet 50, remove the last layer, so include top equal false, and then we add our classifier, which is a very shallow, if you want, neural network. It's not technically shallow because it's more than 3, but it's fairly shallow, that just does recognition for this 10 classification, let's say, for these 10 things. So the network is able to extract the shapes and the contours of a certain thing, vertical or horizontal. It's trying to get the colors. It's able to do all of this thanks to the ResNet. But then, if it has to know if it's a truck or an automobile, it's thanks to this last layer that it's basically a new neural network that we plug in. And that's what we train. So in this case, since this is already being trained, we do not need to retrain it at all. We just need to train this shallow network. And this can be done on my laptop if you want. It's so less invasive and compute hungry than training the whole ResNet just for this task. And that's the magic of transfer learning, basically. I was trying to do this also with the distribute part. So this, I think, should still work. I was doing something slightly more complicated than the strategy. You can learn everything about how to distribute data across GPUs on the TensorFlow example. There are links on basically a training on how to distribute stuff. So I'm not going to tell you everything about it because it's kind of out of scope. But that's basically what you do. You define the strategy, you define the strategy scope, and you compile the model with the strategy scope in it, and that's it. And you just train the model and evaluate. I think this should work. I haven't tested it, so if it doesn't work, don't be too angry at me. But this should work. Let's see here. Yeah, it's downloading the data set, which is provided by TensorFlow. Basically, TensorFlow allows you to download it seamlessly if you want. I'm not sure it's doing it because sometimes inside the compute node doesn't let me download stuff. But let's give it a moment just in case it works. Okay, now we are in PyTorch and we enter this. We enter the examples and we go to this. And this is also distributed. So here is going to be a little faster. We have basically the GAN with distributed support. So we can do it in one shot. Again, let's look at the code. This depends on the data set that we have. We're going to use the MINST data set because that's what we've been using so far. And here is the fun part. So the main difference between TensorFlow and PyTorch is that TensorFlow will run by default on the hardware that finds more suitable. So if you compile TensorFlow, install TensorFlow for ROCm support or CUDA support, and you have GPUs available, it will use them. It will not ask you anything. You have the only way you have control over that is to mask the GPUs available with that flag rocker visible devices equals -1. At that point, you force TensorFlow to run on CPU. But if you don't have that, it will run on GPU by default. PyTorch is a little smarter, and by default, it will run on CPU. And if you want to run on GPU, you have to say which device you want to do it. So let's say you have this. I'm not sure what this MPS means because I'm not a PyTorch guy, but you can query the layer and say, okay, if the CUDA version, the CUDA option was passed, then the device I want to run on is the CUDA 0. Note that everything in PyTorch, even if you're running on AMD hardware, it's called CUDA. CUDA stuff, Nickel. What the approach that an AMD embraced here is to not change anything from what you have already on CUDA. If you have a PyTorch model and it's written with all this CUDA stuff, you can run as is on our hardware. It's automatically EPIfied if you want. You don't have to change a single character of anything, which is great in my opinion. But it can be a little confusing for users when you say, well, I'm not really running CUDA, I'm running ROCm. Doesn't matter. Under the hood, it will do it for you. So you can keep CUDA as is. This is just the number of GPUs that you want, and we'll see in a moment how this works. Here is what I mean by when I say that PyTorch is very much object-oriented, because generator for the fake images, let's say, it's a class. It's not functional. The discriminator is another class. It's not functional. Everything it's a class. Everything it's an object. Sorry, and you have to deal with object-oriented programming more than what you actually need in TensorFlow. So that's the big difference. Another thing is that you have to use this to device if you want to run, for example, on GPUs or other devices too. You have to explicitly say, all right, you need to move this model, which is the discriminator, to the GPU. And this again is the discriminator class. And you see that when forward is basically what you do when the pass forward of the machine learning for the learning phase. This allows you to run on multiple GPUs. That's one line. That's pretty nice. Neural network, parallel, data parallel, and you can run it like that. This is pretty much the same approach that TensorFlow embraces. So you have same model, same structure for each GPU. The data will be different. And then after the training phase on the batch, they will synchronize to exchange the gradients, and that will keep going. Does it make sense? It's pretty much what we have seen with TensorFlow, just slightly different syntax. And that's it. That's all it is. There you have the Adam optimizer, and then you have your epoch loop, and then you have your training loop, backward propagation, forward propagation, the loss function. Pretty much, it's almost a one-to-one match. It's just slightly different syntax. In the original version, this is I modified it to make it a little less heavy on the system, on the file system. It will dump every 100 iterations some data on the disk, like saving the images to see how it proceeds. I didn't do that. I just said, no, just keep going and let's see how the performance is. All right, let's see how it is. I want to show you some differences on the, sorry. All right, this is something that I tested yesterday. I was just testing stuff. Okay, this is already downloaded. You have to download the stuff. Actually, it does it automatically, but if you want, you have to provide this data route where the database will be. Oh, I ran out of time. Let's see if I can get it again. 2 hours have passed. This will be a bummer if it's not. I think we are done. Sorry about that. It's the reservation was just for 2 hours and just ended.
Do you want to try reservation ENCCS _3?
This?
Yeah.
Nope, I cannot do it. Is this MI250? Or is this partition fine?
I thought it was MI250.
So it's the number 4 today, number 4. ENC _4.
4, okay.
It's a 4 day.
I can't count.
Nice, okay, thanks. Here we are. Of course, we have to go back here. Cool, now we are on the right node. Good, thanks, guys. All right, source. Okay, here we are. Again, data set, 1 GPU, 3 iteration, and batch size, let's just do it 256 just for this simple case. We do this. I'm passing -- CUDA. And what we notice here is that PyTorch is not as stupid as TensorFlow. It takes just what it needs, 2%. So that's the good sign here, that PyTorch is slightly more efficient than TensorFlow in that sense, less greedy. And we are basically running. It's, 1 GPU is enough for filling it. this is doing the training. It's doing quite fast for the batch size. You know, it goes up and down, but it's still very, you know, the batch size is not big enough. We can do better. The recommendation is to increase as much as possible the batch size on the GPU to fill as much memory as possible, so the GPU has enough load to actually exploit the computing capability. So 256 is kind of small, and we're using just 2% of the RAM. So the GPU is not really being used all that much, as you can see here. Just wanted to finish so it doesn't. Okay, good. Let's try 1024. And you will see that, of course, there are less iterations because we have a bigger chunk that gets done of the data set. We had just 59 iterations. And it goes better. It's, you know, you see that there is more RAM utilization, and, you know, the GPU gets utilized more, usually. 100% gets stuck more often. And there is some, you know, stuff that needs to be done after each iteration, but we are pretty good. We are going pretty fast, and the GPU is well used. I'm just gonna, I mean, I want to wait again, but because if I stop it in the wrong place, the GPUs will stay allocated, which is something that we don't want to do. Okay. So now I want to do just 2 iterations, so it's a little faster. And I'm going to do 8. And I'm going to do 5,000. So this is the structure of the 2. This gives you a summary of the generator and the discriminator, how they are composed. But what you will see is that the 8 GPUs will have memory allocated in sequential way, almost. All right, 1% on all of them. And it should grow pretty fast. Yeah, 4%, should go up to 5, I think. And that's what's up. It's pretty good. And that's how you scale, basically. You have a data set that is 5,000 big on each different GPU, and then at the end of each epoch, they each iteration, not each epoch here, they will synchronize each batch, and that's it. It's done. That's very nice. You can do up to 10,000, I think, and you'll see some more usage. And it will go slightly slower, but it will have less iterations per epoch on the batches, because you have less batches because they're bigger. Okay, 1% is getting stuff set up. And we should go up to 10, I think. Yeah, there you go. And it's going. Yeah, it's so fast that it has already finished 1. Yeah, that's how it goes. So hope this will help you with your workloads. This is just, again, 1 node. You can do it on multiple nodes, but it's more complicated. There are various ways to do it, and we need some more infrastructure to do this, as you may imagine. But it's there. Support is there. It's ready to go. And as you have seen, it's nothing different from what you're used to with TensorFlow or PyTorch with on CPU or with the competitor. It's pretty much seamless. Are there any questions? I'm pretty much run out of examples. Like, we can do other things here, but it's the same stuff. It's nothing different. Yeah, I'll be happy to take any questions.
There's another question in HackMD. In machine learning, was this one already answered? Does model mean the neurons or neurons with the correct weights?
The model, it's not even the neurons. So a model in deep learning is the one we have seen, and I can show it here. This is a model. A model is a combination of layers, like a convolution 2D or a dense layer. It's followed by an activation function, which in this case is the leaky ReLU, which gives you nonlinearity to the model, which is extremely important, and other things like batch normalization or some dropout for regularization to avoid overfitting the model, and all packed up. So each layer can be different neurons, and they are connected with the next layer in an automated way, thanks to PyTorch or TensorFlow. So the model is the whole package. Each model is composed by at least one layer. One layer is composed by neurons, and then there is an activation function that, if you want to do something useful, has to be nonlinear. There is a theorem that says that if you do not put nonlinear activation function between layers, 10 layers, 100 layers, infinite layers of linear combinations of them is equivalent to one layer. So you have no more representation power in a neural network if you do not add nonlinearity between the layers. That's the power of the neural network. It's stacking different layers that are basically, they have an activation function that it's nonlinear between them. The more stacking, the more representation power you have. It is usually better to have a deeper, and deep means more layer. That's why it's called deep neural network. It's better to have a deeper network than a wider network. So it's better to have 5 layers of 64 each than 2 layers of 124 each, if that makes sense. So depth is better than width.
So Alessandro mentioned this application catalog at the beginning of his talk, and it lists a lot of different tools and libraries. And I do want to note that many of these things have different levels of support. There is a machine language page that lists some of the ones that Alessandro talked about, but some of these others may be interesting to you if you're doing a development of some sort of application. So we have a bunch of solver libraries that are available that do utilize the AMD hardware. So you can sort of break these down into solvers, into sort of low-level support libraries for applications, block structured, AMR, AMREX, and tools, so profilers and such. So we have HPC Toolkit, we have PAPI in the tool categories, higher level programming languages such as Cocos and Raja. This is not a complete list, and the level of support varies a bit across all these tools, but you might want to check that out if you're going to be doing some development and see what can help you write your application faster by using some already developed tools. Now, I think it's time to turn it over to Thor. I think you want some feedback. And these kinds of things are things that we could also solicit more training on in the future.